Zoom's input field is space sensitive.
What is?
Zoom's password. All right, I think we're live, like for real this time.
All right, let me try to advertise this on Twitter or something.
Do you want the exact link or you already have it?
I found it.
You found it? Great. All right, I think we're live, like for real this time. We're good. All right. I'll step away from the camera for like 3 seconds and maybe get some fresh air, and I'll see you in a bit.
Sounds good.
Shall we get started?
Hugo, you're ready?
Yes, indeed.
All right, thanks everyone. So we're now resuming with the invited talk session. It is my great pleasure to have Hugo Vincent from ARM giving us the invited talk today. We have a tradition at PriSC of having industrial members give us a little bit of a wide-ranging, broad perspective on their take on
I think we lost your audio. Oh, you're back.
Dayan, you need to mute your YouTube live stream because I'm hearing myself back. I'm hearing myself better. Okay, good. Apologies for the mishap. So I would say okay, it was on my end. I'm sorry. I had YouTube somewhere that was not closed. Okay, so very happy to have Hugo Vincent give us the invited talk today. Hugo is a principal research engineer at ARM in Cambridge, and his research has been spanning both the hardware and the software. He's worked on both the processors and the software through the embed library. And I think you should have a pretty interesting take on secure compilation. So thanks, Hugo.
Thanks, Jonathan. Yeah, it's my pleasure to be here this afternoon. And this is my first time at PriSC, and in fact, my first POPL as well. So very excited to be here, and go easy on me, please. All right, so as Jonathan introduced, I'm part of ARM Research. And for those who don't know, well, I'm sure most people here know who ARM are. We design primarily compute technology and CPUs. And I'm part of ARM Research, which is an organization of about 180 researchers based in Cambridge in the UK and Austin, Texas, and a few other sites around the world. I'm part of the systems group, and I lead the security efforts in ARM Research. So the talk I'm giving today is basically some perspectives on trends and things that I think are interesting in secure compilation, and some of the work we're doing in the space, and kind of sort of around the space. So yeah, to get started, wanted to talk a little bit about some sort of macro trends to frame things. And hopefully none of these are going to come as a huge surprise to anyone, but I think it's useful just to sort of set the context a bit by running through them quickly. So one thing that those of us in the hardware industry are talking a lot about these days and for the last couple of years is the fact that manufacturing technology, chip manufacturing technology, progress is slowing, and this is called the end of Moore's law. And the free ride that, and I use that phrase in air quotes, the free ride that the industry had for 20 or 30 years, sort of starting around the early 90s, was, you know, every 18 months transistors got smaller, faster, lower power, and cheaper. And that is no longer the reality. There's still progress being made, but it's typically, you know, pick any two, or maybe if you're lucky, pick any three of those four desirable traits. So the result of that is that there's an increasing prevalence of hardware acceleration for a wider range of tasks. If you look at especially a mobile SoC like in a smartphone, that's kind of our bread and butter at ARM. If you look at a die shop for one of them, you know, increasingly the CPUs are kind of just a little dot in the corner, and there's a whole sea of all sorts of other hardware accelerators, you know, GPUs, neural network accelerators, and all sorts of other things. Within the CPU and kind of in the world of kind of like traditional software, there's an increasing role of architecture and an increasing responsibility for software on optimization rather than sort of the brute force approaches or expensive abstractions to hide problems. And the last kind of macro trend is that security by most measures is getting worse. And this kind of confluence of all of these trends is is the challenge that we're facing, and that's where I think the role of secure compilation is becoming incredibly important. So thinking of compilation abstractly, you know, lowering and mapping of programmer intent to execution hardware, the job of a compiler is getting much harder, right? There's more pressure on performance by the slowing of Moore's law and the you know, the lack of increasing frequencies and increasing IPC that have been the norm for many years. And at the same time as that, you know, there are larger instruction set architectures with more sophisticated features. The ARM architecture reference manual is something like 8,500 pages at this point. So there's a lot of stuff at that hardware software interface that the compiler has to know about just at the CPU. And then you've got all of that other range of diverse execution resource I mentioned. And, you know, I guess we traditionally don't think of a compiler as targeting all of that at once, targeting that sort of heterogeneous set of execution resource, but abstractly that is kind of in the realm of a compiler's job. And then on top of all of that, there's a much longer and increasingly long list of security concerns that the compiler is either kind of complicit in or has to take responsibility for addressing. And then on top of all of those, you know, if you hang around in a hardware company or go to a hardware industry conference or something like that, you often hear people saying phrases like, "Oh, that's just a software problem," right? And I think the last couple of years, you know, since when was it, 2017, it's been really interesting being in that world as Spectre and all of the sort of deluge of related microarchitectural side channel attacks have come out. And I think this has highlighted the need for cooperation and collaboration between hardware and software communities. And if you think about it, you know, the hardware software divide, what sits on either side of that, one side is the compiler and one side is the ISA, right? That's why we at ARM and ARM Research are really, really interested in this, this domain of secure compilation. Many security mechanisms have a significant performance cost. I'm talking about both software and hardware security mechanisms here. And in many cases, this is due to conservative assumptions, right? You kind of, as an architect or as a developer, you think, what's the worst case here? And you sort of bake that in as a conservative assumption. And now that's a safe thing to do, but with those headwinds I mentioned on the previous slide, around performance pressure, we are being forced to revisit some of those assumptions, right? So putting all that together, secure compilation promises a way forward. You know, abstractly allowing programmers to specify security intent at the programming language level, and having the compilation technology automatically exploit new hardware security features that the hardware is exposed, and you know, verifiably map software onto hardware using specifications, requirements, and variants and so forth exported by the hardware. This is kind of the holy grail, I guess, if you want to look at it that way, and I'll come back to that towards the end. So those are some of the trends to kind of frame things. I wanted to give a couple of motivating applications and use cases for why, from an ARM perspective, secure compilation is important. And then I'm going to talk a little bit about some recent investigations we've been doing in the research group. Okay, so motivations. So the first one I'm going to talk about is confidential compute. And this is kind of a buzzword that's starting to show up all over the place in over the last sort of 12 months or so. Confidential compute is about securing data in use. And this is in contrast to kind of two of the traditional notions we think about in terms of security, which is securing data in transit and securing data at rest. So securing data in transit is a fairly well understood problem, you know, by no means easy, but fairly well understood. And things like crypto protocols, such as TLS, are kind of the tools in the toolbox. Likewise, securing data at rest is fairly well understood. You know, things like encrypted storage in databases and verified boot and that sort of thing are relatively well understood. Securing data in use is in general not so well understood, or not so universally understood. It is counterintuitive, right? How do you operate on data while keeping it in a, for example, encrypted form? There are cryptographic approaches that exist, right? Like fully homomorphic encryption, but these are severely limiting, either in computation model or in performance. There are some, there's a lot of momentum building around trusted hardware and trusted execution environments as a way of achieving data security in use and delivering confidential compute. And this, in a way, is kind of building on some of the kind of constrained applications that have enabled this technology that are now widespread, such as DRM for protecting media. As I say, this is kind of a buzzword that's been gaining momentum quite rapidly over the last year. This was an article in Spectrum last May saying a handful of major technology companies are going all in on this new security model called confidential compute. Arm is one of those companies. And one of the ways we're doing that is through our participation in the Confidential Compute Consortium, which is a Linux Foundation project with quite a wide range of member companies, including both ARM and Intel, and which I guess represent the most common computer architectures, and then a number of the major cloud vendors and other hardware and software vendors. And this is focusing on securing data in use and accelerating the adoption of confidential compute openly. It's an open source project, as you would imagine, under the Linux Foundation. So why is this kind of hyping? It is a very powerful thing. The capability of doing confidential compute enables computation on sensitive data on machines you don't control or trust. So you can offload compute to the cloud, to the edge, to other people's computers without allowing them to have, carte blanche access to that data. And there's a whole lot of reasons why that's a good idea, from the kind of regulatory, like GDPR and HIPAA compliance, to, increasing need for things like cybersecurity and cyber breach insurance and the requirements that insurance is posing, through to kind of increased commercial and consumer awareness of the value of data, the sensitivity of data, and, maybe a little bit more utopian, sort of the desire to empower privacy sensitive users and applications to benefit from all of this progress that's been made over the last sort of decade or so in cloud and edge and distributed architectures. And I think, I don't want to I'm trying not to overhype this, but confidential compute promises to finally unlock the full vision of sort of distributed compute as a utility, or kind of grid computing as it's often called. And I think that's pretty exciting. There are two main ways of doing confidential compute, and both of these are deeply reliant on secure compilation in rather different ways. And I'll talk more about both of these ways later on. So the first way, as I touched on earlier, is cryptographic approaches, canonically fully homomorphic encryption. And these are great because, the security properties of crypto are fairly well understood and fairly, you can write them down and communicate them quite easily. And you just have to trust the maths. And once you trust the maths, then you can put the computation anywhere and you don't have to figure out whether or how to trust it. The current state of the art in fully homomorphic encryption has a number of downsides. Most pressingly, I guess, as performance, which is typically around 10 to the 5 or 10 to the 6 times slower than native code. And in fact, it can even be more than that, depending on what the code's doing. And the other sort of major downside is the computational model is quite restricted, and we'll come back to that later on. The other approach, the one that's kind of gaining momentum a lot at the moment, is trusted hardware. And this is kind of a compromise. This is not as idea, it's not as philosophically a thing as the cryptographic approach, but it's a bit more pragmatic. And the idea is to use jointly trusted hardware locked down under jointly agreed upon conditions. And the way this is done is through kind of 3 bits of technology. One is trusted execution environments, which are hardware-backed sort of isolation mechanisms within a larger system. The second is remote attestation, which allows the remote party, the relying party, so I guess Alice in the case of these diagrams, to to gain strong assurance of the state and the contents of the trusted execution environment on the remote party, on Bob's computer in this case. And then the third one is sandboxing technologies, and this is about protecting Bob's computer from potentially a malicious program by Alice in this case. So using these types of approaches, the trusted computing base can be greatly reduced, but you know, the reason I say it's a pragmatic compromise is there's still, all parties still have to trust the correctness of the underlying hardware and the low level sort of software and firmware that makes this possible. And, you know, one of the things that would be nice to have, but doesn't exist and most probably will never exist, is a way of kind of hashing physical material, right? Like you can't, you know, there's nothing analogous to a cryptographic hash function for the physical processor chip that you're running on, right? And so there's a degree of trust involved. Okay, I'm going to come back to that in a little bit. The next thing I wanted to talk about is a motivation for secure compilation is cryptographic software, and we've heard a lot about that earlier this afternoon in the other PriSC talks. Cryptography is just such an important thing, right? It's how we establish trust in distributed systems and in the internet. And I think, you know, the last 12 months with many of us being forced to work from home has kind of highlighted the importance of that more than ever. Another reason cryptographic software is important and worth protecting is I was actually just looking at I was reading a news story about Bitcoin the other day, and I was staggered to see how much that's increased in value in recent times. And the chart on the slide here shows the total volume of all Bitcoin in circulation at the current price and how that's evolved over time from 2013 to the present. The market capitalization is now around $700 billion US, which is quite a lot of money. And if you're an attacker and you think that some of the software, right, because software implements this, some of the software that implements this this cryptocurrency might be vulnerable to attack, and you're willing to either be criminal or unethical about it, then there's an awful lot of money to be made here. So cryptocurrencies are a good reason to care about secure compilation of software. The next motivating thing I want to talk about was system software. And, you know, in communities like this, I think we often talk about privileged software, OS kernels, hypervisors, debuggers, that sort of thing. I think the reason those are important is self-evident. I wanted to talk about some of the others that I don't see talked about so often. The first one here is firmware and early boot software. And this software, like privileged software, right, is incredibly high privilege. It happens first thing out of boot, out of reset on the hardware. And it typically has all of the capability, all of the privilege that exists in the system. And it's responsible for configuring the hardware correctly, working around silicon bugs by disabling faulty hardware. These are so-called chicken bits, and then bootstrapping into nicer software. And this is super high privilege and super important because everything that happens after it and the chain of trust relies on it. But it's often pretty hacky and under-documented code, especially the code that works around hardware faults, which are often not publicly documented at all. So that would be an opportunity for improving things. The next one is performance governors and controllers. These have started to make their way into the security literature over the last 2 years through things like the Clockscrew and Plundervault attacks. So these are bits of software that are responsible for managing clock and power and thermals in a chip. And it is now the case that pretty much any CPU chip, whether it's in a mobile or a desktop or a server, is having to actively manage clock and power and thermals. So there is software that runs that has the potential to permanently damage the hardware it's running on. And there's the potential for hardware to betray the software by, for example, breaking abstractions or allowing maluse to inject faults into software or to introduce side channels. So that's another really interesting thing that would benefit from secure compilation. And then the last one on here is kind of firmware for non-CPU hardware. I talked about in the macro trends at the start, the increasing heterogeneity and diversity of all of the stuff on a chip. And all of those things that aren't the CPU are increasingly self-contained and smart, and most of them run their own firmware. Most of them can generate memory transactions that bypass most of the software protections that exist, and even the highest privileged software like the hypervisor on the main CPU. And some system level defenses do exist, such as IOMMUs and a bunch of other related things, but often these are underutilized in current systems. Okay, so in terms of, so that sort of wraps up the motivations I want to talk about. The next part is about some of the things that we're doing that I thought might be interesting to this community. So the first one, just very briefly, is on hardware capability architecture. And this is trying to attack the problem of memory unsafety. Memory safety remain the dominant source of security bugs. They are primarily due to the fact that a lot of software is written in C and C++, and C and C++ memory safety is a mess. So 2 bits of data here, one from Google in 2018, basically saying more than 50% of high and critical severity bugs in Chrome and Android are, have a root cause of memory safety. More recently, I just pulled this quote from the Chromium website. The Chromium project finds that around 70% of our serious security bugs are memory safety problems. And likewise at Microsoft, Matt Miller gave a talk in early 2019. Matt's in their security response center at Microsoft. And the chart here, it's probably a little bit small, but the chart is basically a categorization of all of the CVEs that Microsoft have patched from, I think, from 2006 to 2018. And the dark blue is memory safety related and the light blue is non-memory safety related. And you can see over that period, from all the way back to 2006, there's a remarkably stable kind of 70% of vulnerabilities are kind of on average stemming from memory safety. So this is a mess, and it's kind of been a mess for a long time. As ARM, we've tried to address this in a few different ways. In recent versions of the architecture, we've added a few features that help patch some types of memory safety issues. So we've introduced things like pointer authentication codes in, I think, ARM v8.3 and a memory tagging extension, and I think it was in ARM v8.5. Those are good, and those will eventually, I presume, show up in devices like phones and so forth, and hopefully help. But we were interested in seeing if there was a way of attacking that problem more at the root cause. And to that end, we've been working with the Cherry project, which is a development of the University of Cambridge and SRI that they've been working on since about 2010, and we've been working with them since about 2016, I think. So Cherry is a set of new hardware and ISA extensions that introduce some new features. I'm trying not to use the word capabilities here. And I'll go through them in the next few slides, but we've been doing 2 kind of research investigations around Cherry. One of them is called Morello. This is now quite public. And there's 2 links here if you're interested in more information. Morello experimentally extends the 64-bit ARM architecture with Cherry. And the 64-bit ARM architecture, as you probably know, is what's used in Cortex-A and Neoverse cores that are in, a majority of mobile phones and quite a few infrastructure applications and so forth. Under the DARPA SIF program, we've also been looking at adapting Cherry to microcontroller applications for deeply embedded systems. And that's looking really promising. We haven't yet published anything on that work, but we are excited about the results we're seeing there as well. We think Cherry can drastically improve security for much of the software in today's systems and can span ICEs from the cores and microcontrollers to data centers. So we're excited about the potential here. There's still, these are both still very squarely in the research realm. Morello's quite a bit further along, and they're actually building an experimental test chip, which I believe will be available around the end of this year, I believe. And that's going to be made available to researchers and so forth. But these are still in the research kind of realm at the moment, because Cherry is quite disruptive. So what is this kind of capability architecture? So a capability is defined as an unforgeable token of authority. It's kind of a bearer token. So possessing one is taken as authorization to use the resource it relates to. And Cherry applies this, mature concept. The concept of capability has been around since I think the 1960s or so, and it applies it to memory. So pointers are replaced with capabilities, and all access to memory goes through capabilities relating to each allocation of memory. And the capabilities use a hardware tagging mechanism to achieve this unforgeable property that's a requirement. So there's a hardware memory tagging and provenance control mechanism to ensure capabilities can't be forged by, for example, writing arbitrary bits to a capability. If you do that without using the correct sort of provenance preserving instructions, then the hardware clears the tag and it's no longer a capability. Capabilities, as well as the address, right? These are replacing pointers, as well as the address, they carry bounds and permissions with them in a kind of fat pointer, if you like. Software basically shrinks and subdivides capabilities and hands out smaller allocations. So you can imagine, for example, malloc might be given at the start of the process a capability for the whole heap, and it carves out and returns smaller capabilities for each allocation when it's called. And these features in Cherry, the bounds, the provenance control, and a number of related features combine to address memory safety vulnerabilities. Yeah, those last 2 points just say what I said on the previous slide. So how do they work? I mean, I'm not going to go into a huge amount of detail here in the interest of time, but just to kind of illustrate it really quickly, imagine you have this really horrendous function that takes in a username and copies it into this fixed length buffer. This, as everyone here probably knows, is a really bad idea, and it's pretty trivial for an attacker to exploit this by passing in a much longer, strict copy, looks for a null terminated string, and it'll just keep copying until it hits that null. So you should really use something like str end copy, which would stop copying once it hits the bounds. But anyway, a lot of software looks like this, and this is kind of a canonical memory safety bug or vulnerability. By replacing the pointers here, like myArray and username, with capabilities, so this gray sort of stack here as a representation of the stack, the C ABI, as you probably know, typically puts the return address on the stack as well. So when you enter this function, you push the return address, and then when you get to here, the compiler allocates this myArray on the stack. And when you call strict copy, it gets a pointer to here. And if you pass in more than that 100 bytes, it'll keep growing up this way until it overwrites the return address. And once you overwrite the return address, you have control. You can point it anywhere you want and start executing arbitrary code. Capabilities prevent this sort of attack in 3 ways. Firstly, the bounds prevent the overflow itself. Secondly, the provenance control I mentioned allows you to detect that the return address has been corrupted and prevents you branching to it. And branching to data or the middle of functions is prevented because the wrong permissions would be set on the capability that would point into this area. And by itself, these protections don't stop all memory safety attacks, but they do go a long way to breaking exploit chains, which is how a majority of complex vulnerabilities constructed these days, where it's not just one vulnerability, it's a whole series that are chained together, and you just have to break one link in that chain to break it. So capabilities are exciting, and the work we're doing with Cherry is exciting and promising. And if you're interested in learning more about that, check out the Morello project. There's a bunch of open source resources available on that now. I think there's a public simulator and documentation and compilers and so forth. And we hope that that technology, the Morello technology, demonstrates enough value that it becomes part of the future mainline ARM CPUs. All right, so that was the first part. The second part, how am I doing on time? Okay, I'm gonna have to speed up a bit. Second part is towards verifiably constant time crypto on ARM CPUs. So the starting posture here is the functional behavior of a CPU is well specified. We have this ARM reference manual, the architecture reference manual. It's quite a beast of a document, but it's fairly exhaustive, and that defines the hardware-software contract. And if you look in it for each instruction, in this case, add with carry, there's pseudocode that describes the operation, and this is a formal specification of the behavior of the processor. This language, the ARM specification language, has formally defined semantics, and you can kind of dig into exactly the operation that the instruction set architecture says the processor is performing here. And you can interactively explore this. There's a few open source tools like ASL Interpreter, and all of the pseudocode here and all of the functions that are called by them, that's all publicly released as part of the A-profile exploration tools. So you can download a big tarball of all the XML files and so forth, and import them with MRA tools into ASLI and sort of interactively explore what the ISA is doing or claims to be doing. And this is part of a wider ecosystem. So a lot of this work was done by Alistair Reid, who used to be at ARM Research. He's now at Google. And this was, there was a POPL paper 2 years ago, which I encourage you to read if you haven't already. Some more work around this is being done by Peter Searle's group at the University of Cambridge through their SAIL project. And both the ARM architecture and the Morello architecture can be incorporated into the SAIL flow, and using SAIL, you can convert that into a whole bunch of different forms. You can generate documentation, you can generate prover definitions, you can generate simulators, you can generate tests, you can bring it into SMT, and a whole bunch of other things. So that's all great. Formal ISA specs and tooling let you ask and answer questions about what the instruction set architecture says it's supposed to be doing. And you can do all sorts of cool things with that. But what about timing behavior? Because recall, for crypto code, as we saw in earlier PriSC talks, you actually need to care about the timing. And the right way of doing crypto code is so-called constant time code. Now, to write constant time code, you need to restrict yourself to instructions that have timing behavior that doesn't depend on the operand values. So if you look at, let's say, signed divide instruction or unsigned divide, they have a latency that is dependent on the operands. So you shouldn't use these instructions in crypto code. Well, what about add and multiply, for example? Well, those look a bit better, but there's a but. I'll come back to that. So these are in what are called software optimization guides that publishes for each processor, for each of our different microarchitectures. Intel does the same. I believe other CPU vendors do the same. I'm not proud to say, but I think Intel's documents do a much better job of giving a disclaimer around these numbers. They say that the numbers in these tables are approximate and subject to change in future implementations in the microarchitecture. That there is a big red flag, right? Because if you're relying on these numbers when you're writing crypto code, those are subject to change, and it could go from constant time conceivably to non-constant time. And that would make code that was safe now no longer safe on future hardware. In this case, this was the data for a Cortex A76, which is a typical, this would be a big processor and a big little cluster in a mobile. there's also little cores in the clusters as well, maybe an A55. And in this case, this multiply instruction that was constant time on A76 actually has a variable timing depending on the operand data. So if you're doing a 64-bit multiply, where the top half, the top 32 bits are not all ones, then it will take 3 cycles, and if they are all ones, it will take 2 cycles. So there's data-dependent timing behavior on this processor. Again, that's not ideal if you're writing crypto code. And as I said, these are often paired together in a big little cluster. So if you're not familiar with this term, this is when you have a heterogeneous collection of processors, typically just 2, but perhaps that'll extend in the future, 2 different types of microarchitecture, high performance cores and sort of efficiency oriented cores. And the operating system will dynamically move tasks between these cores at runtime based on the needs of the system and some of that, performance management stuff, thermals, power, etc., and user experience that I mentioned earlier. And with increased pressure to deliver performance in the face of end of Moore's, this sort of thing is only going to get worse. So, it's conceivable future systems may have more than just 2 types of microarchitecture. It's conceivable and likely that you'll see the operating system moving tasks around more often and in more cases. And if you're relying on this timing behavior we talked about here, that's a problem, because when you're running here, you're constant time, and when you get migrated here without anyone telling you, because the operating system decided you didn't need a high performance core, then you're no longer constant time. And so what's really going on here? Well, the architecture defines what happens in terms of the functional behavior, but it says basically nothing about timing behavior, and this is by design. This is because architectures want long-term software compatibility. So they want software written today to work on a processor 10 or 20 years from now. And as architects, you naturally aspire to clean orthogonal abstractions, but below the level of the ISA, microarchitects need freedom to innovate within the envelope of permitted behavior. So the ISA defines an envelope of behavior, and the microarchitecture is the specific instantiation of a CPU on a particular chip. And microarchitects can and do wild things to get better performance. And if you were surprised in early 2018 when Spectre came out that a CPU could do all of those things that it does in terms of speculative behavior and so forth, then this is an example of some of the things that microarchitects do to get better performance. By and large, the operating system and most of the software only concerns itself with architected behavior. And in principle, because the functional behavior of these 2 multiply instructions was the same, the operating system's free to move your process from one to the other. In the 8.4, I think it was, we added a bit to the P state, which is one of the system register for processor state, and it basically allows software to query whether or not the hardware has data-independent timing support. So there's as defined in the ARM, there's a set of instructions that are said to have timing behavior that does not depend on the operands or the flags or certain other things when this data independent timing bit is set. So if you're writing crypto code and you're relying on the timing behavior of instructions, this is something you should be looking into. And this is low-hanging fruit in a way. This is, most of these instructions like add and Boolean operations and so forth are ones where most sane hardware would implement in a constant time way anyway. But again, it's about the contract between hardware and software and ensuring that the assumptions that you're making in your software are valid assumptions that will still be valid on future CPUs 10 or 20 years from now, because we know software has a habit of sticking around for a long time, right? So I think, as we've seen in some of the other talks, writing constant time code can have a large performance impact compared to unsafe code. Some examples, that people do in their constant time code when they're doing crypto is, they might emulate floating point using bitwise operations and so forth, because the hardware doesn't typically implement floating point instructions in a constant time way, especially for things like denormals and so forth. And more generally, if you really care about constant time, you can do things like transforming code into circuits and bit slicing and so forth. This data independent timing bit we added is just a sort of low hanging fruit, a first step. And I've kind of listed some questions to the community, right, for the secure compilation community. How would you like this to look? How would you like this to evolve? What kind of invariants and guarantees would you like CPUs to be able to make? Right, with the data independent timing, we don't guarantee that these instructions are constant time. We just guarantee that their timing doesn't depend on the operands or the flags or certain other things. And that, we think, is a useful abstraction for reasoning about and writing this sort of software. But there's a whole bunch of other questions, and we'd love to hear from the community on some of those. All right, the last part I wanted to talk about is confidential compute. And I see I'm doing even worse on time now, so I'm going to have to speed up. I think I might actually just skip this bit on FHA. We can come back to it, perhaps, in the questions. Okay. So I talked earlier about confidential compute and cryptographic approaches and trusted hardware. We're interested in both of these. We're just about to start a project under the DARPA DPRIVE program with a number of collaborators looking at hardware accelerating these sort of things. But the focus really has been on trusted hardware, and I wanted to dig a little bit into some of the things we're doing there. So we have a project in research called Veracruz, which is about doing private delegated compute, like I talked about earlier. So this is kind of the software infrastructure you need for doing these sort of workloads and applications on a variety of currently available trusted execution environments, including TrustZone and Intel SGX. Veracruz has a number of kind of components. So first off, there's a sandbox where programs run inside the enclave. And the sandbox is implemented using WebAssembly as the sandbox. So programs are brought into the enclave as WebAssembly programs, and a WebAssembly runtime is used to sandbox these functions that you want to apply to confidential data. Veracruz also has infrastructure for performing attestation of the state of the TEE, measuring its contents and conveying those measurements to the relying parties. And it has a sort of a policy framework for allowing data owners and program owners to specify how their data and programs should be used, permissions, identities, that sort of thing, what should happen to the output. So the space we're sort of living in with Veracruz is we want to have a framework for efficient multi-party computations in the same kind of vein as things like FHE that I talked about. But we aim to be efficient, so fast enough to execute real interesting programs, familiar, so programmers can use tools they're familiar with, general, so they're not limited in the computation model, and reusable, so that library functionality and so forth can exist without everything having to be done from scratch each time. And we aim to do all of that while still delivering similar security and privacy guarantees to what you get with these cryptographic approaches, subject to the hardware trust things I mentioned earlier. So we have an abstraction over isolates, and we currently support 3. We have an ARM TrustZone based TA isolate. We have Intel SGX enclaves, and we have an implementation of SEL4 on AH64 as a micro hypervisor that can be used to create isolates as well. And these kind of exist on a continuum of paranoia, if you like. Credit to my colleague Dominic Mulligan for coming up with this phrase I really like. from the kind of really paranoid, where you really, arguably really only have to trust the CPU itself. In the case of SGX, just the actual chip itself, that implements a whole bunch of mechanisms like memory encryption and integrity protection and stuff to try and make that possible, through to maybe slightly less paranoid cases like software isolation using a formally verified microkernel with fairly rigorous security and integrity properties. And we abstract over these and add a programming model based on WebAssembly and an attestation mechanism based on ARM's PSA. That's the Platform Security Architecture Protocol. There's a bunch of things that we're currently working on and thinking about. So in the vein of kind of secure compilation, we want to go further with WebAssembly. We think WebAssembly is really interesting as a kind of intermediate representation for secure compilation, because one of the goals with a confidential computing environment normally is to minimize the amount of stuff in the trusted computing base. So having a compiler, for example, and all of the software that supports that within the enclave is, somewhat risky, because that's a large volume of software that could potentially have vulnerabilities and an attacker could exploit. We want to minimize the amount of stuff in the TCB, but we don't want to necessarily just allow arbitrary machine code binaries to be run inside the enclave, because that would, in the absence of other sandboxing mechanisms, that would create a risk of a maliciously crafted binary potentially compromising the other contents of the enclave. So we're interested in exploring other ways of doing sandboxing, for example, with Morello, when that hardware starts to become available. We're interested in how you can deploy sort of microarchitecture specific mitigations for things like Spectre variants and so forth, without having to recompile from source to WASM. So by changing the way that we generate the machine code from WASM, or the way that we interpret that WASM, we hope to be able to deploy mitigations without having to have the software author go back and recompile their source level program. There's a bunch of other things that we're working on there as well, but I think I'll skip forward in the interest of time. So Veracruz is open source. It's on GitHub. We've only been there for a couple of months, and we're excited to be doing this research in the open after, being in secret and secret labs for a long time. And we're excited to have submitted submitted Veracruz as a CCC project to the Confidential Computing Consortium. And that's, I believe, been accepted, although I think there's a little bit more paperwork to be done there. Okay, looking forward to the future, I see secure compilation as a vital technology. I'm looking forward to a future where programmers can capture security intent directly alongside their high-level programs in a high-level programming language, where hardware can export specifications describing the security features it has, the microarchitectural side channel behavior it has, and so forth, where owners of data can determine and define policies limiting and specifying how their data is used and shared, and where next generation secure compilation technology can pull all of that together, those policies, the specs, and the programs, and automatically generate verifiably correct, secure, and performant binaries. Now, I think we have a long way to go on all fronts. I hope you agree with me, and if not, I'd love to hear why this future is closer than I think. But I'm really excited to work towards this goal. I think this is an incredibly exciting and high potential area, and looking forward to hearing the rest of the talks this afternoon at PriSC. Thank you very much. Let me pull up the chat and see if there are questions. All right. Okay, question from Andrew Myers. How do you know if the actual implementation of the ISA correctly respects the DIP? Okay, so that's a great question, Andrew. There are a few things there. So I guess is, has the hardware vendor correctly implemented the ISA? If there's a spectrum of responses here. I think a lot of people would point to open source hardware as potentially a solution to this. I don't think that's quite right, or at least I don't see it as a complete solution, because assuming you're running on an actual, piece of silicon that's been fabricated in a foundry and not running in an FPGA, for example, you still have to trust that the manufacturing of that chip has been done correctly. So it's true, like software cannot guarantee that the DIP bit is being, has been implemented correctly. You have to trust that, but in fairness, you have to trust almost everything else about a CPU, right? How do you know that the add instruction adds to things? Well, you can look at it. You can perhaps even exhaustively run through all possible pairs of operands and check it, but are you really going to do that with every instruction? It's a complex question. All right. Next question's from Anitha. What kinds of policies are you looking at in Veracruz? Currently, what we have in the open source project is fairly shallow in terms of policies. They are limited to things like identities and authorizations, so fairly shallow policies. We would like to extend that, and I think one really exciting project in the space is the Google Oak project from, I think, Google or DeepMind Research, and they're also an open source project on GitHub, and they've been doing a lot of really interesting work in terms of building tools and technologies for allowing individual end users and data owners to write sort of quite expressive policies. So I'd point you over there if you want to check it out, and we hope to head in that direction with Veracruz as well. Okay, question from Dominique.
Yeah, please make sure you read the questions, because this is broadcast to YouTube, and YouTube doesn't see the text box of the Zoom call. Thank you.
I see. Okay, thank you. The next question is from Dominic, which is, you haven't talked about how Cherry enables fine-grained software compartmentalization. How do you regard the importance of this with respect to mitigating memory vulnerabilities? Okay, yeah, so it's true. I didn't talk about fine-grained software compartmentalization. I only talked about Cherry for memory safety. One of the other things you can do with Cherry is you can build, as you say, fine-grained compartmentalization mechanisms based on the same capability concept. And I would say I regard this as high potential in the sense that I think this is really important, but I would say in terms of empirical evidence we have at this point, we've done a lot more work, and the Cambridge and SRI teams have done a lot more work on the memory safety side of things. And we have a lot more confidence that that works, that actually does achieve what it says it's going to achieve. I think software compartmentalization is really exciting, primarily for a reason other than memory, for mitigating memory vulnerability. I find it exciting from a performance point of view. And one of the promises that the Cherry team talk about is using the Cherry compartmentalization mechanisms to unwind and back out some of the older isolation mechanisms we use in software today. So to give an example, most web browsers now use a whole set of different processes for isolating tabs from each other. Processes are good, they offer a fairly high degree of isolation and separation, but they're pretty expensive. Context switching all the time, all of the TLB, invalidation traffic and so forth, and just TLB thrashing in general. So I think these mechanisms are exciting, and that they allow you to do sandboxing in ways that are potentially higher performance than some of the things we do today. Okay, next question. Does Veracruz already support a secure multi-party computation framework on top of the TE? If so, which one? Short answer, no, it doesn't. We don't use one of the existing out-of-the-box sort of cryptographic multi-party computation frameworks. if you have a suggestion, we'd love to hear it. And if you can point us at something, that would be great. The approach has been to just allow, you know, programs written in Rust or C or whatever you can define, you can compile to WASM. And we've got a sort of utility library of a few little bits and pieces for helping you implement multi-party type computations in that way. But yeah, if you have a suggestion on a framework, I'd love to hear about it. All right, next question. Oh, this was a clarification from Andrew by the looks. So my question is more about whether the hardware designers have the tools to check it for themselves rather than about malicious foundries, etc. Okay, so yeah, that's a good question. There are hardware design, so ARM obviously designed CPUs that implement our architecture, and we do have a set of tools and methods that we use for checking those sort of properties. I'm not sure if your question is about CPU designers like ARM or more about like an SoC integrator who's taking ARM cores and building a system on chip out of it. Okay, both, Andrew says. Yeah, I think there's an opportunity for improved tooling here. And actually, Andrew, I think the work your team has done on things like chisel flow and stuff are really, really exciting. And I think there's a lot of potential to improve the way that hardware is tested and developed using those sort of approaches. Next question is from Marco. It seems that some of your future plans, like support for better constant time against Spectre-style leaks, require a more precise hardware-software contract tailored towards security. Do you believe that ARM, Intel, other manufacturers are willing to commit to such contracts given the constraints of how the microarchitecture can evolve? So yeah, absolutely. You've hit the nail on the head there, Marco. That's the big challenge, right? I think I said on one of the slides, we are still trying to find a way of doing that, and we'd love feedback. I don't believe have, and as far as I know, no one has the right sort of abstractions and the right way of writing specifications that would be useful to relying parties, like people writing crypto code, but also are flexible enough to allow microarchitecture to evolve in the ways that we care about. And I should add, you know, we build ARM CPUs ourselves, but a lot of other companies also build their own implementations of the ARM instruction set. So it has to be suitable not just for us, but also for our architecture partners. Hope that answers the question. I think that's it. If there's any other questions, please let me know.
All right, there doesn't seem to be any other questions in the text box. I've also checked Clouder and YouTube, and I don't see any other questions. So thanks, Hugo, for a most excellent talk. That was very illuminating. Here's how the rest of the program will go. I think we can take just a 4-minute break for those of us who need it, and then we will remain in this Zoom call and restart with the next session in like 4 minutes. So we will start on formal analysis and proof techniques in this call. All right, I think we can resume for the third session of the day. I will be moderating the first two talks, and Marco will be moderating the rest of the talks. We are staying in this Zoom room. I've tried to post the information as well as I can on Clouder and everything. And hopefully one of the student volunteers might be able to dial in into whatever different room is linked in for the Nanopass talk and make sure that no one is stuck in the wrong room. All right, so it's my pleasure to welcome all of you to the third session of the day. We will start with a talk by Jérémy Thibault and Katalin Chitko on Nanopass back translation of multiple traces for secure compilation proofs. And as always, remember that you can ask your questions in the Zoom text chat. Diane, feel free to go ahead and play the video. Thanks.
Hello, I am Jérémy Thibault, and this talk is about our ongoing work on mechanizing and simplifying secure compilation proofs. It is well known that building a secure compiler is a difficult task, and even harder is proving it secure. Even then, existing proofs are often hard to trust, because they can span several hundred pages, and are very brittle, as one tiny mistake might make the whole thing collapse. Hence, we need to work on developing new proof techniques that are both simple enough to be mechanized and that can be reused. As a first step towards solving this issue, we present a new back translation and a new proof technique to show its correctness. This technique is implemented in the COG proof assistant as a replacement of the back translation step of an existing secure compiler for a compartmentalized language. This allows us, without modifying the compiler or any other proof, to show that the compiler satisfies a stronger criterion than what it was previously shown to. Moreover, we believe the back translation can be reused with little modification, as it relies on very common features of programming languages. The back translation and its related proof use ideas that were originally developed in the field of compilers. That is, we define several intermediate representations of the traces that must be back translated, each carrying more information than the previous one, and each with their own semantics. The back translation is then designed as a Nanopass compiler targeting the source language, and is proven correct by proving multiple, simple, COMSORT-like forward simulations between the different representations. To make this idea clearer, let me show you the criterion that was previously shown. Given a source program that, when compiled and linked with a low-level context, produces a trace M, one can exhibit a source context that can be linked with the source program to produce the same trace. However, this criterion can be a bit disappointing. It does not capture key properties such as non-interference or relational properties such as observational equivalence. We make the criterion stronger in the following way. Instead of considering a single program and a single trace, we now consider several programs and as many traces, and must build a single context that will work for all of these programs. The proof technique we use is very close to the one that was used for the previous criterion. First, the traces are back translated into a source context and several source programs that produce them when linked together. Then, using a combination of compiler correctness and of a special step called recomposition, we are able to obtain the result we aim at. Luckily, we can make the following observation. All the steps except back translation work pointwise, and they can be directly reused from the previous proof without any modification. We are able to prove the stronger criterion simply by changing the back translation step. I'm now going to present the new back translation, but first I need to give you more details on the trace model and on the previous single trace back translation. The traces record interactions between compartments that belong either to the program or to the context. For instance, here, compartment C1 first calls compartment C2 with argument 8 that calls compartment C3, that returns 17, etc., etc., etc. To satisfy the requirement of the theorem, given such a trace, we must build compartments that will reproduce the trace, event by event. Look at C2, for instance. The first event it must produce is a call to C3 with argument 13. In the code, we look at the number of events done variable to know how many events have already been executed by this compartment. If it's 0, we update it, because we are about to produce one more event, and produce the appropriate call. Similarly, if one event has already been processed, then the next event must be a call to C1 with argument 22. And finally, the third event will necessarily be returning 32. One of the reasons this backtranslation works is that each event in the trace contains enough information to construct one of the branches of the program, and that the next event is uniquely determined by the position in the trace. However, that's not the case for our new criterion using several programs. Consider this example where on the left the context C2 is linked with the same program as before. On the right, the same context C2 is linked with a different program. On the left, C3 returns 17 after being called. On the right, C3 prime returns another completely different value. Then, the single context C2 is now allowed to behave differently, because it receives a different return value. On the left, it still calls C1, but on the right, it returns some value instead. Hence, the backtranslated context we construct will need to distinguish two different executions in order to know what to do. In our solution, we see the set of traces as a tree of events. Here is the tree corresponding to the previous diagram. Backtranslating such a tree is not as easy as backtranslating a single trace. Indeed, the context must always know its location in the tree. First, each node must be assigned a unique identifier, and the context must be able to branch and return values to update its location correctly. A counter is not enough anymore. Worse, it's not enough to simply look at the very next events. Let us make our example a bit more complex by adding a third program that branches off at the same point. In this third branch, instead of immediately returning, the program first performs a callback before returning. Hence, getting the information necessary for the backtranslation might require deep search inside the tree. Finally, note that there are now two returns to the same call with the same return value. The backtranslated context must be able to distinguish between the two, and so needs to keep more information. All these reasons make it so that the backtranslation as a single step is hard. It requires writing a complex function, and proving its correctness is hard as well, as we need to deal with complex invariants. Hence, we propose to simplify the backtranslation by dividing it in several easier steps. This is what we call a Nanopass backtranslation. The backtranslation is divided into several steps, each taking trees and transforming them a little so they become closer to the final backtranslated program. Our steps can be split into two groups. Preprocessing steps go through the tree, adding more information to each node, such as what its parent is or what return values it can expect. A second phase happens when we start generating source expressions. Their role is to deal with particular information. There is one expression that will process the return values. There is one expression that will emit the new event, etc. These expressions are still kept in a tree, so as not to lose all the structure yet. Eventually, all is flattened into a single expression for each compartment, obtained by plugging the previously generated expressions inside the dispatch table. I will now describe one of these steps that deals with the problem I evoked earlier. After returning from a call, how do you know what the new position in the tree is? For this, we need to know two things. First, the last location just before the return, and second, the return value. For instance, let us look at how we add this information to the second node here. If we take the left branch, the return is immediate. The last position was that of the call, 2. The return value was 17, and the new location is 3. If we take the middle range, we are also immediately returned 2. But this time, the new location is 7, and the return value is this big number. On the other hand, if we take the right branch, the return is not immediate. The return 17 appears at location 11, and the previous location was 10. Using this information, we can now, in a later step, build an expression that shall be executed after returning from this call. If the location is 2 and the return value is 17, then the location should be updated to 3 according to the table. If the location is 2 and the return value is 22564, then the new location should be 7 according to the table. And if the location is 10 and the return value is 17, then the table says the updated location should be 11. Now, to prove our back translation correct using these steps, we need to define for each some semantics. As the basis for these semantics, trees are reduced in a small step manner to produce the events they contain. For instance, to reduce the tree on the left, we simply eliminate its root, emit the event it contains. But this is not all that happens when the tree contains more information. Indeed, the enriched semantics for this language make use of the added information in the nodes to enforce explicitly invariants that were only implicit in the initial trees. For instance, let's look at the tree with return information from before. To reduce it, we must indeed eliminate the root and emit the event it contains. But this is not all. The semantics use ghost state to store information about the current execution. For instance, this ghost state contains information such as the last seen location and a stack. When executing a call, the semantics update this ghost state so that the last seen location is up to date. Before it was 1, now it's going to be 2. And they push the table containing return information on top of this stack. For now, this information has not been used, but it will when doing a return. Indeed, a return will only be allowed by the new semantics if the return value, the old location, and the new location correspond to an entry in the table. Then and only then can the root be eliminated, the event emitted, and the ghost state updated by updating the last location again, and by removing the top of the stack, since we just did a return. Here, the semantics enforce a well-bracketed call return discipline, and enforce the fact that returns are going to be caught and the correct location updated. To summarize, we make the implicit invariants of the execution explicit by making sure that the semantics enforce them. To close the proof, we must now prove forward simulations between representations. In the end, via transitivity, this implies that the traces produced by the initial trees are all produced by the back-translated programs. During the preprocessing phase, proving a simulation amounts to proving that the preprocessing step we are considering is correct. The information added to each node in this step is enough to prove the new invariant induced by the semantics. During the code generation phase, the simulation's roles are different. There, the generated expressions are partially executed against the source semantics, using a new concrete state. The simulation ensures that the ghost state and the concrete state are kept in sync. In the end, this approach was successful because it allowed us to reason one step at a time. Very often, the changes between two representations are very little, and this makes the simulation proofs very reasonable, which was not the case when we tried the monolithic back-translation approach. Finally, we believe that the proof can be partially reused. The earlier steps that only deal with adding information to the tree should be completely independent. The later step would also be reusable given a bit of work, since they only use patterns that are found in most languages. To summarize, we describe a way of back-translating multiple finite traces into whole programs using private state, and we implemented it in Coq. We show how we can use the Nanopass approach and the existing framework of concert simulations to simplify the implementation and the proof of correctness of the back translation. The back translation can be reused, as it is not very language specific. One of our current goals is to prove that it is indeed possible by extending it to a more complex language. Another parallel line of work would be to study how to extend this kind of proof to languages with different trace models. For instance, ones where some state is shared between compartments. Thank you.
All right, great. And do we have, yes, we do have Jeremy here. So I'm going to make sure I read the questions for the people who are on YouTube. So Dominic De Vries has a first question. Your technique of back translating a context from a number of interaction traces, that is, not taking into account the syntax of the context itself, can be seen as an alternative for syntactically back translating the context itself. Do you expect your approach to be easier in all circumstances, or are there situations where the alternative is better?
So I think it should be easier as long as you're able to work with finite traces. As soon as you need to deal with infinite executions, so for instance, if you want to prove something like a full abstraction in a non-deterministic case, then you need to deal with infinite traces, I believe, and then I don't think you can easily back translate infinite traces into a single finite program.
Okay, great. Moving on to the next question from Marco. In terms of generality, does it make sense to replace the usual call return actions with a generic jump? What about actions that happen between question mark and exclamation mark actions? Do they make sense in a generic back translation?
So actually, so I'm not sure if I understand correctly the question, but in our trace model, we really record calls and returns. And I guess if you wanted to replace them with generic jumps, you would have to be able to distinguish jumps that correspond to calls and jumps that correspond to returns. Or
Marco, feel free to jump in if you want to clarify your question.
Yeah, so I was just indeed wondering whether it's always relevant to have indeed like the nature of the jump, like a call and the return can be seen as two different jumps. And I was wondering if in your experience, like applying these, when thinking about the generality of this proof technique, do you think like knowing that one is that a jump, let's say back from the component to the context, knowing that it is a return rather than a call, does it actually play a role, or would knowing that just having just given the control back to the context, is that sufficient as in the case of a jump? Because for example, like in assembly, you could also have just a generic jump, right, between code parts. So what would that become? Does it then make sense to have call, return, and jump like a go-to?
So I'm not really sure. So first, it doesn't fit into the trace model we consider here, where we are really able to distinguish calls and returns. But if you instead wanted to use jumps, I don't think there would be an issue with always having jumps.
Okay, cool.
All right, thanks, Jeremy. And let's keep moving. We should now move on to the next presentation, which is by Marc Gourjean, Explicit Leakage, Handling Side Channel Behavior, and Program Rewriting and Analysis. Dan, whenever you want for the video.
Hi, welcome to this talk. My name is Marc Gourjean. I'm a PhD student working on side channel resilience, and in this talk I would like to focus on the branch of secret compilation which is targeting side channel security. So this branch is about determining, establishing, and preserving some formal property which is defined over the side channel behavior of a program and targeting specifically this side channel behavior of programs. An example would be observational non-interference, where this behavior, the side channel behavior of this program under consideration must be independent of secret or sensitive data. In this talk, I would like to introduce you to the concept of explicit leakage, which introduces a new construct in a programming language to express the side channel behavior of a program. And in this talk, I will use the leak statement for this purpose. And this gives the ability to separate the semantic specification from the representation of side channel behavior, and in the end allows to facilitate program transformation and analysis. We have used this in a recent work for verifying the security of masking, one countermeasure, in user-supplied models of side channel behavior. Let me quickly recap side channel behavior or side channel leakage. When a program is executed on a physical device, this physical execution causes side effects. Among them are well known the timing of instructions or the timing of memory accesses from cache timing, leakage, resource consumption, for example, the power consumption of computations, or physical radiations like electromagnetic radiation, sound, heat dissipation, and so on. These behaviors are usually defined for formal purposes in the leakage models and is usually a subset of the actual behavior, but it's important that this leakage model encapsulates the whole behavior considered. In this talk, I will focus on data-dependent timing, but just to exemplify the concept of explicit leakage really works for a wide class of side channel behaviors. So on the right-hand side, you see a program which takes some value x, multiplies it by a secret value, and writes it to a temporary variable, but does not return anything. As you might imagine, that multiplication by 0 or 1 is significantly easier than multiplying by a large prime number, for example, and therefore the timing of multiplication might be dependent on the operands. So for this instruction here, or this operation here, you can imagine that the time it takes to compute it depends on both values x and the secret value on the right hand side. The point I would like to make is that in practice there is a very large and diverse set of leakage behaviors or side channel effects. These are usually architecture specific or even device specific. One example is the timing of multiplication, where here this table from a cryptographic developer indicates that for older ARM devices, the timing of this multiplication from two 32-bit values to one 64-bit value was timing sensitive, that is dependent on the inputs. Whereas for recent architectures, it's quite okay, except for the Cortex M3, where it's apparently still sensitive to timing attacks. So far this is already a bit diverse, but the fun part really comes with RISC-V, where we have one common instruction set architecture which can be implemented by different communities or vendors, and therefore we might see a lot more diverse side channel behavior. Furthermore, it's not only about multiplication. This is just to exemplify. This also holds for memory accesses, cache architectures, vectorized instruction sets. And think of AVX, ARM, Neon. There are lots of extensions which possibly have distinct and diverse timing or other side channel behavior. This diverse set of leakage behaviors we encounter in practice is a bit in conflict with the goals of secure compilation, which is on the one hand to have good security assurance from the formal notions, and that means that the leakage model must consider this diverse behavior, and on the other hand, the goal of having slightly efficient implementation, which means that on the Cortex M4, the supplied hardware multiplication instructions should be used, whereas on the Cortex M3 it must not be used. And this is also in conflict with the traditional way of modeling these leakage behaviors. In the traditional approach, usually leakage is tied to semantic. That means that in a domain-specific language, every construct or every operator encodes a specific semantic and a specific side-channel behavior. This means to encode the behavior which is different on M4 and M3 for the same multiplication, multiple multiplication operators have to be introduced. So in this example here on the right, I'm showing that with different colors that the same multiplication is performed with operands E1 and E2, and to execute the step, they have distinct side-channel behavior as indicated by the arrow in the middle. That, for example, for the red multiplication, which should somehow ideally be representative for the M3, the operands of the multiplication E1 and E2 impact the side-channel behavior or determine some side-channel behavior. And clearly this is not optimal, because to encode a lot of different diverse leakage effects or leakage behaviors, many operands or operators and constructs are introduced, and each of these variants has to be handled. And also the transformation is always tied to these specific behaviors. There's a way around this, and this is explicit leakage, and brings me to the main topic. So the suggestion here is that we separate the specification representation of side-channel behavior from semantic by introducing a new construct, which I will denote leak. And so on the right-hand side, you see this dedicated construct, leak, which takes a number of expressions. And the idea is that the expressions in the leak statements define or represent the program side-channel behavior. The remaining part of the language can now remain free of side-channel specification and specifies only the semantic behavior of programs. Now, with this dedicated construct, different variants of side-channel behavior can be encoded without introducing additional operators. So if we take again these three distinct multiplications, each with a different side-channel behavior but with the same semantic, these can be now expressed with the help of two statements. One in the second line is always the semantic specification, being that C is being assigned the multiplications result of E1 times E2. And then the different side-channel behavior can be indicated with this dedicated leak statement, which in the first case, in the first column, to say expresses that the side-channel behavior in this program depends on the values E1 and E2, or the expressions. This is quite flexible, so the behavior can quickly be adopted for the second case, where the behavior, this artificial example, only depends on the second operand, or a third case where there is no data-dependent side-channel behavior, and therefore there is no side-channel specification. The concept is really flexible in encoding different behaviors with just a single leak statement, and that's also the key point of it. There's a single construct to specify side-channel behavior, and all the remaining operators remain free of specifications of side-channel behavior, and therefore we don't need any variants anymore. This will also facilitate the analysis later on. There are ways to abuse this slightly, just to give you an idea, to say that on function return, there might be a residue on a stack or in a heap, and a dedicated leak statement might be used to say that the side-channel behavior of a program depends on these values left in the stack, if you wish to. The concept is really flexible and applies to a lot of different side-channel behaviors, and also allows to specify, for example, memory leakage, or memory leakage arising from memory accesses. So the meaning of the leak construct, to summarize, is that each expression in the leak statement defines the side-channel behavior of a program, or represents the side-channel behavior of a program. And on the other hand, leak has no side or semantic effect. It's purely meant to specify the side-channel behavior. And the converse is true for the remainder of the semantic, which is purely semantic or side effect specifying and not specifying any kind of leak statements. To take the question where these leak statements come from up front, this is up to you or the user of this concept. One way is to insert leak statements during lifting of input program to intermediate representation, or to perform this annotation during the instruction selection. And another way would be to have a dedicated transformation, which is, for example, done by EasyCrypt, where the leakage behavior of a program is extracted and made explicit. The treatment of leak statements is specific to security notions. Think of observational equivalence, which says that the two programs must be exactly equivalent in the terms of their leak statements, which might also mean that the order in which leakages happen must be the same. So in this case, it is not okay to reorder leak statements. Whereas in k-anonymity, for example, which is relevant for masking, the order does not matter, but the number of leak statements is relevant. Something I will just mention here at this point is that it is important to keep the binding of leak expressions, leak statements to their semantic cause, as we will see later on. Let me now dive into transformations and show how the concept of explicit leakage facilitates analysis and transformations. To do this, let me introduce a small domain-specific language which consists of expressions and statements, expressions of variables and multiplications of expressions, and the statements where we have an assignment, so a semantic action, the specification of side-channel behavior through the leak statement, and a special construct to bind two statements to each other. So ASOC is meant to say that that one statement cannot exist without the other. So S1 cannot exist without S2 and vice versa. This is used to keep the binding between leak statements and semantic cause intact. So we can re-specify the leakage behavior of multiplication as we had it before. On the right-hand side of the association here, we have the multiplication being assigned to C, and then on the left-hand side we have a leak statement to encode diverse sets of leakage behavior, which can be altered quite flexibly. As a first transformation, I would like to introduce a liveness analysis pass, which computes not only which variables affect outputs, but also computes which variables affect side-channel behavior in a program. And this is quite easy since we have a dedicated leak statement. The analysis can be made aware of leakage and tag all the variables which are used in leak expressions. For the assignment, it is just as in a common case as if there was no leakage behavior in the program represented, because this assignment and the expressions are free of side-channel behavior. And finally, there's this association, which is in this regards just a sequence operator, and therefore the liveness analysis is performed on both statements. Based on this, secure code elimination can be performed. The idea is that elim tags those statements which can be removed. And for the assignment, it's the usual case that if the variable being assigned to is not live, then it can be removed. But for the leak statement, as we want to preserve observational equivalence, it is never removed. Now, if we consider our program, just those two rules would allow to remove the multiplication here on the right-hand side, but would not remove the leak statement. This would be okay for analysis, but since the causing operation is now removed, this might get into trouble if we look at later on passes which come later on, for example, reordering or lowering. So therefore, the ASOC is used to bind leakage and semantic actions, and therefore prevents that one is removed without the other. This can be quite easily be adopted, for example, to remove secret independent side-channel behavior and not preserve observational equivalence. And this is simply based here on taint information to remove leakage when it is not secret dependent. To summarize, the concept of explicit leakage really allows to specify a diverse class of leakage behavior, and the transformations are becoming largely independent of the actual behavior considered. This is quite nice. This is the good part of it. On the other hand, the association between leakage and semantic has now to be maintained, and this, I think, can be improved. Finally, handling of the leak statements remains specific to the security notion, and I think this is just in line with the focus of secret compilation anyway. Thank you.
All right, wonderful. And we have Mark, who's online to answer any questions.
Hi, yes, can you hear me?
Yes, your audio is good. All right, so I'll read the first question. Marco asks, in simple cases, leak statements look rather neat. How would one capture more complex leaks, such as leak a value under only some conditions or more complex microarchitectural leaks? Would everything need to be encoded in terms of program code?
So this is the way we have done it in the paper I mentioned in the beginning of the talk. There we actually had, for the power side channel case, leakage which depends on the instructions being executed before. So in the end, maintaining a history of behavior to some degree and then leaking combinations across this history and the current instruction. And this works, and we have done this in this way there by indeed performing it based on the programming language where we represented the program in. I'm not sure how you would do it differently than encoding it in the intermediate representation. Probably this works. But yeah, so we have just used the intermediate representation for this purposes. And this works quite nicely since we had in our case a partial evaluation anyway, which was removing then those occurrences.
All right, thank you. Do we have any other questions anywhere? Zoom is clear. I don't see anything on Clouder, and I don't see anything on YouTube either. Okay, so we were running a little bit late, so I think it's a great opportunity to thank you once more for your talk, and I'm going to hand over the chair role to Marco. Marco, are you with us?
Yep, yes, I am. Hi, hope you can hear me. Okay, let's roll with secure optimization through opaque observations.
I'd like to present a concept of opaque observations and its applications to secure compilation and more specifically to secure optimization. So this is joint work with colleagues from Sorbonne University, ARM, and ST Microelectronics. So let's maybe start with a very common effect in secure compilation, which is referred to as within weeks. What you see is not what you execute. Has been also very popular in studies about like debugging, software engineering, etc. And as probably the simplest example possible in secure applications, you may consider the remasking or the cryptographic mask switching problem. The challenge here is to make sure you never unmask the key. So whenever you apply a new mask, you have to XOR it with that new mask before XORing again with the original mask. With the fact of removing the first mask. But the problem, obviously, is that compiler transformations may not respect this priority. The compiler may notice that these are associative and commutative operations, and first unmask, like applying the XOR with before applying the new mask, and this is obviously unsafe. So this is well known. People are dealing with this kind of problems. This is just one problem among many. That optimizing compilers feel that they are entitled to this kind of transformations. And a typical approach, there are many approaches, but the typical approach is to trick the compiler. So it's not necessarily to design a new compiler from scratch or new optimization passes that would be sensitive to every single kind of security property that we care about, but it's to try to trick the compiler and live with it. For example, in this case, introducing a volatile variable may work in some cases, but as you can expect, this is fragile. So a better approach is to try to make this property we want to preserve explicit, and obviously also to instruct the compiler to preserve that property, not only at the source level, but also preserve that property through the flow. And one additional challenge we take is we don't want to design a new compiler that has these capabilities. We want to make this the least intrusive possible, and instruct a production compiler, in this case LLVM, to behave properly in the presence of security properties like this one. So that's why we bring this concept of opaque observations. So this is an intuition that many people have had, essentially people implementing these tricks to protect security countermeasures. And the idea is that you want to make the compiler aware of some values that have to be computed in a particular order. So there are two properties here. One is some values have to be computed. They have to be there in the first place, whatever transformations are applied downstream. And you also want to make sure that those computations follow some partial ordering. In this case, the example is very simple. So there's basically only one observation you want to make. So one value you want to guarantee to observe. You can imagine that in more complex examples, and I don't have time to show you such examples in detail, there would actually be sequences of such observations, and the ordering these observations take is also important. So the semantics questions we are facing here is how do we make such an observation robust to downstream transformations, and also how to make this compiler independent. And that's where opacity comes in. So you want to make sure that there is a concept that every compiler implementation following some basic definitions of like correctness or validity of the transformations would actually preserve this observation. And opacity is one way to hide the information that you want the compiler not to analyze as a contract between the programmer and compiler. So we introduced a very simple semantics that's inspired by LLVM, but it's also capturing abstractions slightly higher level than LLVM. So you have it's an operational semantics with state and transitions that we call events. The state capture SSA values, also general references, memory, and the program counter that you use to track the state transitions. The events are labeled with an instruction. One of the highlights of this semantics is that we really focus on I/O. So we consider that what really matters in a secure application is not so much its computations in a functional sense, but more in interaction with the environment. These interactions can be ordered, like think of streaming I/O or network communications, etc., or unordered, think of persistent storage. And the semantic correctness is defined with respect to these input and output effects. Because of this ordering of effects on input sets or output sets, depending on the type of input and output, we also induce the partial order on I/O events. So whenever we would talk about semantic correctness, we talk about preserving these I/O effects and also the partial ordering among the events. So the semantics defines the function as expected from inputs to output sets, and it also defines some kind of trace. So we call it an execution, which is an alternating sequence of state and events, and we are going to review what happens to an execution across program transformation. So that's the one of the keys actually of the approach we are proposing is to try to define what happens to program transformations without identifying a specific program transformation. So we want to be as general as possible, and we want a notion that can encompass basically whatever a compiler could do while preserving semantics, even speculative transformations, very dynamic things. So the only assumption we make is that static transformations preserve I/O and the partial ordering of I/O events, as I said. On top of that, we associate every transformation of a program P into program P prime with a so-called event map, which is a relation that relates events before and after transformation. So this relation has to also relate I/O events before and after transformation. So we define additional rules, obviously, because this is a little bit weak without more information about this map. But we're going to use this map, this event map, to prove properties of transformations with respect to the observations we want to preserve. So let's talk about observations. In brief, an observation is defined formally as a partial state. So think of a snapshot of the state of the semantics by focusing on some specific SSA values or references or memory we care about. In addition to this snapshot, we established a contract between the security expert, the programmer, and the compiler, which is that we want the compiler to preserve three things on the observations. We want to make sure that whenever an observation is made before transformation, it's still happening after transformation, except the code dies, for example, because it's not useful downstream. We want to be able to trace the observation down to machine code. So this is very important for some applications such as testing, monitoring, verification of the binary. And we also want, as I mentioned earlier, to preserve partial ordering constraints. So the same way we have ordering on I/O, we want also to preserve ordering on observations. And this is important because programmers, as I said earlier, want to make sure that some observations follow some partial ordering constraints. In order to establish this contract, we define a happens before relation that the programmer has control upon. So this happens before relation will be enforced by the compiler. We're going to see how. And so obviously it includes the I/O ordering relation, which we call I/O, because it has to be for correctness reasons. But it also has to enforce two observation-related relations. Observed from, which is related to the use of an observed value, has to be preserved, and observation ordering, which essentially captures data and control dependencies over observation events. So HB, that happens before relation, is the union and transitive closure of these three steps. I don't have time to detail exactly the definition of these, but you get the intuition. The problem here is that I/O is preserved by construction, but the compilers like LLVM have no clue what an observation is. I mean, they are not meant to preserve observation. Opacity is the way we are going to trick the compiler in a robust way, in a sound way, if you want. Again, this is something that people have played with using existing like compilation mechanisms, like separate compilation, for example. But here we make it a first-class mechanism. So opacity is introduced as a single entry, single exit region of the control flow. We can have whatever like uses, computation, side effects, I/O within such a region. The only hypothesis is that it terminates. And program transformations are bound to some constraints with respect to what they can do on these opaque regions. So atomicity and isolation. So this is pretty obvious. You don't want transformations to interpret some I/O or some effects in the middle of such a region, and vice versa. And beyond that, you also want the compiler analysis to be limited in what they can do about opaque expressions. So they can figure out what variables are used. They can figure out whether an opaque expression has side effects or has I/O effects. But it's not authorized for a compiler to go beyond that. It's not, for example, possible for a compiler to figure out the exact side effects of an opaque expression. On the other hand, the compiler can decide the fact that two opaque expressions are identical, and that's it. There's basically nothing else the compiler can do. In this case, we don't have theorems. We have actually some hypotheses. So we have axioms that describe what compilers can do in the presence of opaque regions. The first one, intuitively, so don't read the math here, but intuitively, the first one is that the event map must relate opaque events. So events associated with opaque expressions, as soon as they are connected with data or control dependencies. So it's a little bit more subtle than that. I have a next slide on this, but as soon as there is some dependent relation between two opaque events, and one of them is, I mean, the consumer is preserved, is mapped through the transformation, then the producer also has to exist. The intuition for this is that you're not going to manufacture a value produced by an opaque event, by an opaque expression, because it's opaque. So whenever it's consumed, it also has to be produced. And a similar thing with the values themselves. So whenever a value is read from or is used from an opaque expression, it has to come from that exact opaque expression. So basically, the expression has to exist. The opaque expression has to evaluate in the transform program. It has to be mapped through this event map relation. And this is the exact same value that you're going to read. We are going to use these dependencies, so these control and data dependencies among opaque regions, to build so-called opaque chains. And those opaque chains are going to be the architecture, basically, for enforcing partial ordering of observations. And also for enforcing the preservation of the observations themselves, because we're going to use these opaque chains to link individual observations with I/O instructions, which cannot be eliminated. The intuition is that those opaque chains are very much chains of data and control dependencies, but there is a little bit of subtlety due to transformations like conversions of data dependencies into control dependencies and vice versa. Constant specialization, which can break dependencies by just enumerating all possible values of variable, and also instruction combining, which can merge multiple paths in the control flow and eliminating duplicated instructions. So intuitively, you can think of some minimal information has to remain on some opaque values so that the compiler cannot just get away with the opaque value completely and predict statically what's coming. So the applications of all of this are essentially in side channel and physical attacks. So whenever you have countermeasures like security properties implemented at source level, and they don't immediately translate into I/O, but they are there to present semantics that's not functional. That's actually coming from physical attacks or interactions. So I listed a few here, and so key remasking is one. Erasure of secret data obviously is well-known problem with dead code elimination. Control flow integrity, and more specifically a few problems related with fine-grained instruction level integrity, and also loop trip count integrity, so checking that you have the right number of iterations before exiting the loop. These are the kind of problems that we can protect using these approaches. And also constant time selection, which is well known to suffer from downstream optimizations that may replace carefully crafted constant time expressions into branches, because some compiler backends know that in some specific microarchitectures, it's actually faster to have a branch than a conditional move, for example. These are things we can avoid using this opaque observation approach. So we have an implementation of this in LLVM, which with minimal changes. That was one of our challenges, our goals. We encode some the observations all the way down to the dwarf like mesh encode, and so that you can actually use this information in external tools. We have both functional and performance evaluation, like validation of the compiler. For example, we can compare the performance of using tricks with our approach, which is much leaner in terms of using opaque expressions only at the places where you need to guarantee some values are observed and some partial ordering, and using I/O only in the end, for example, of some functions or some applications. So this translates into concrete performance improvements compared to the state of the art. And so just to summarize, so we have been addressing this within-week effect. So we want to have the correctness of transformations with respect to security properties defined independently of any program transformation of any particular compiler implementation. And this is where opaque observations help. So we define these opaque observations as both observations and opaque expressions. We have a formal model for these, and this model provides stronger guarantees and higher performance than the state of the art.
All right. Thank you for a very interesting talk. Do we have any questions? Either. I don't see any here in the chat. Let me check on Cloud. All right. Well, while we wait for people to type, I'm not seeing anything neither here nor on Clouder. So if I'm missing anything, please write it in the chat here. But for example, do I understand correctly that you are considering from this work from a whole program transformation perspective? So from the correct compilation, do you have any plan to move towards a robust compilation setting? So consider an attacker, a linking of programs with respect to an attacker, and whether interoperation with an attacker could leak, could make optimized code perform any leakage?
That's a very good question. So we have only considered like separate compilation and not link time optimization so far, because we need this opacity property to be preserved and expressed in the IR. So whenever you would use link time optimization, you would have to capture opaque expressions in the intermediate representation you use for LTO. So whether you optimize LLVM IR across modules, that I guess it's going to be pretty seamless. to extend. But if you want to optimize binary code, like at the time, you will have to recover this information from the machine code. So it's, as I said in the talk, it's possible to capture the information using the dwarf format. But how robust this is, really, we have not experimented with. But in theory, this is applicable because the same properties that make the encoding robust to any possible transformation should apply to LTO as well.
Cool. Look forward to the future work as well. Maybe next year.
Thank you.
At PriSC. All right. So in the interest of keeping up with the time, next, and in the spirit of Disney remakes, we have The Fox and the Hound from Carmine and Matteo, who are both in the audience. So let's roll the clip.
Hello everybody, I'm Matteo Busi from the University of Pisa, and today I'm going to talk about comparing fully abstract and robust compilation. This is an ongoing work in collaboration with Carmine Opaque from the Max Planck Institute for Security and Privacy. And as the first thing, let's start by taking a closer look at what we mean by fully abstract and robust compilation in our setting. A compiler is said to be fully abstract if it preserves and reflects contextual equivalence. In other words, if we denote a compiler with these two square brackets that you can see here and here, we want to ensure that two source programs, P1 and P2, cannot be distinguished by an arbitrary source context, which is how we model attackers, if and only if P1 compiled and P2 compiled cannot be distinguished by an arbitrary target context. Instead, with the term robust compilation, we refer to a family of criteria, some of which are known to be strictly stronger than fully abstract compilation. For the purposes of our work, however, we just focus on the preservation of classes of hyperproperties under adversarial contexts, where an hyperproperty is a set of traces that describes the behavior of a program. More precisely, robust compilation in our setting prescribes that if a source program P robustly satisfies an hyperproperty H, meaning that it satisfies it under any context, then its compiled version satisfies the very same hyperproperty H in an arbitrary target context. So far we have two notions of secure compilation. On the left, you can see fully abstract compilation, and we have preservation and reflection of contextual equivalence. On the right, we have robust compilation, which is the preservation of classes of hyperproperties under adversarial contexts. A natural question is under which conditions fully abstract compilers are also robust compilers. And of course, we are not the first to investigate such a relation. And in particular, it has been shown that in general, fully abstract compilers are not robust, not even if one focuses on specific hyperproperties like no-interference. However, fully abstract compilation has been widely successful for the last 20 years, also when considering the preservation of specific hyperproperties like no-interference. These results together suggest that comparing the two notions just by checking whether one logically implies the other is not completely satisfactory. For that, we propose to investigate a different question. The question we try to answer is, given a fully abstract compiler and the program P that robustly satisfies an hyperproperty H, what is the hyperproperty that is robustly satisfied by the compiled program P? Moreover, under which conditions the hyperproperty that the compiled program satisfies coincide with the original hyperproperty? In fact, in the latter case, a fully abstract compiler is also a robust compiler. So again, let's take a look at our current definitions. On the left, we have, again, fully abstract compilation, and on the right, we have, again, robust compilation. First of all, we can notice that fully abstract compilation talks about contextual equivalence. So the blue relation here and the red relation here, which is a relation between programs that is often defined as equiconvergence or equidivergence. On the other hand, robust compilation focuses on the robust satisfaction of hyperproperties that, as we know, are sets of traces. So for any comparison to be possible, we chose to pick contextual equivalence to be trace equality, which is a possible choice, but we leave different choices as future work. The other issue to be solved is that robust compilation only talks about a given hyperproperty H at the source and requires it to be preserved as is at the target. However, we need a slight generalization of this. In particular, we consider a mapping tau tilde between hyperproperties, and we change robust compilation as follows by requiring that if P robustly satisfies an hyperproperty H, then P compiled must robustly satisfy tau tilde of H. We are now ready to state our preliminary results. The first result is quite interesting. It is possible to prove that a given fully abstract compiler is always, in some sense, a robust compiler. In particular, we can prove that given a fully abstract compiler, it always exists a mapping tau tilde such that if P robustly satisfies an hyperproperty H, then P compiled robustly satisfies tau tilde of H. Also, we can prove that tau tilde is optimal, in the sense that if P robustly satisfies an hyperproperty H prime, if P compiled robustly satisfies an hyperproperty H prime, then tau tilde of H is included in H prime. But there's more. On top of the theorem of the previous slide, a straightforward corollary gives us a sufficient and necessary condition to understand if a given fully abstract compiler robustly preserves a fixed hyperproperty. In principle, it would suffice to decide if tau tilde of H is included in H. However, there is still one big problem, the computation of tau tilde. To see why the computation of tau tilde is a problem, let's see how tau tilde works on a given hyperproperty H. First, it takes all source programs that robustly satisfies H, then it compiles them all, and finally returns as a result the set of their traces in an arbitrary target context. Such information is, of course, way too much, and much more than just knowing about the preservation of a given hyperproperty for the compiler in hand. Moreover, such a computation highlights the fact that tau tilde actually depends on the compiler itself and on the language we are considering. To fix this issue, in our ongoing work, we are trying to work around this problem by considering successive over or under approximations of tau tilde, depending on what one is willing to prove. So, assume, for instance, that you want to show the preservation of robust non-interference, which we denote here as an I. By the corollary above, this means that if the compiler is fully abstract, it suffices to show that tau tilde of an I is included in an I. For that, we can successfully over-approximate tau tilde with a family of mappings, as you can see here, F1, F2, Fn, until it becomes easy to show, or actually maybe trivial, that the over-approximation is included in non-interference. If we are interested instead in showing a violation of non-interference, the corollary requires to show that tau tilde of Ni is not included in Ni. For that, we can try to under-approximate tau tilde until it is clear that its nth under-approximation is not included in Ni. Though we have not generalized the approach, in the abstract you can find a small example to illustrate this technique. In particular, the example considers a source language in which programs are lists of assignments and all web-typed programs are non-interferent. The syntax of the target language coincides with that of the source, but its semantics differs, so breaking the non-interference property in some of the target programs. Now, if we take the identity function as the compiler of interest, we can prove that the compiler is fully abstract according to our definition. So the real question becomes, does it robustly preserve non-interference or not? Well, the answer is no. Since we can prove by computing tau tilde of an I by successive under-approximation and show that at some point the approximation is included in tau tilde of Ni, but not in Ni. Thus proving that that tau tilde Ni is not included in Ni, and due to our corollary that the identity function does not robustly preserve non-interference in this particular setting. To sum up, we have shown that fully abstract compilation implies some form of robust compilation parameterized by a mapping of hyperproperties called tau tilde. For more details, you can have a look at the appendix of the abstract that was also partially formalized in Coq. In some very particular cases, our choice that contextual equivalence is equal to trace equality follows from determinacy. Our next step is to generalize this result to other notions of contextual equivalence. Another step we plan to make for this work is to provide a general technique of approximating tau tilde that we showed here to be not really computable and to be compiler and language dependent. Finally, since we are particularly interested in non-interference, we want to explore better what happens to non-interference when it is mapped by tau tilde. In particular, our guess is that maybe under some mild assumptions, tau tilde behaves as a declassification of non-interference. And that's it. Thank you for listening. You can find more details about our work on this link on archive, and we are happy to take any question or suggestion for this work.
All right. I see a raised hand by Stelios. Stelios, I think you can unmute yourself and fire away. Excellent talk, by the way. I look forward to full complete result. It's brilliant.
Okay, can I go? Okay, so hi, Matteo. Nice to see you again. So I really appreciate and like this kind of work. And at this point, I don't have any comment to add, maybe later on. What I want to say is that I think you're going to find some interesting connections with what I'm going to present in the short talks. So I implore you and invite you to stay over, not go to sleep, something else.
I will.
And, okay, cool,
I will
great.
be there.
because those robust properties and this quantification over context, I think you're gonna find some interesting connections here.
Okay, thank you.
Problem.
I will be there.
Do we have other questions or comments, either in the chat or on Clouder? Let's see the second page. Doesn't look. Status, did you re-raise your hand, or I presume?
Just very quickly.
One more.
Yeah, just one more.
Go ahead.
Is your notion of trace equality abstract over internal steps, invisible moves in the last slide, or at this point, no?
Actually, it's an abstract trace equality. We just say we have some notion of traces, and we just assume that the two programs are contextual equivalent if they have the same traces under any context.
Okay, trace equality. Okay, straight up.
In the sense that if you think of fully abstract trace semantics, that's the notion.
I'm really glad that you're saying these words. I think you're gonna like this. All right.
All right. Thank you again for the talk. Thank you, Stelios, for setting up a bit of hype for your talk later on. We can then end the session with the last talk about capability machines by the group at Aarhus University. Alex, I presume you're in the room? If not, someone else? Yep, excellent. Roll the clip.
Hi everyone, I am Alex and I will talk about some work in progress on complete stack safety for capability machines. This is joint work with Annalyn George, Armel Guillenot, and Lars Birkedal. So capability machines are a kind of computers with fine-grained control over memory accesses. And one such kind of capability machines is the Cherry machine from Cambridge University. Beyond being a product of research, capability machines are becoming a real reality, with ARM developing a prototype of a Cherry extended CPU called Morello. And thanks to the fine-grained control over memory provided by those capability machines, they are making a very attractive target for secure compilation. And as such, there has been a lot of recent work on protecting memory, either the heap or the stack, using capabilities. In this presentation, I will mainly focus on the call stack. So the call stack is what is used to implement high-level abstractions such as local state or structured control flow. And if the call stack is not properly maintained, then a malicious program could abuse it to hijack the control flow or leak confidential data. There have been previous work focusing on protecting the call stack to enforce some purposes, namely local state encapsulation, wire-bracketed control flow, and temporal stack safety by those papers on the slide. So what are those purposes? Let's start by explaining local state encapsulation and wire-bracketed control flow with this example known as the awkward example. Its code is given in C on the left-hand side and the OCaml equivalent is given on the right. I'm going to walk through the example step by step. So F first set its local variable x to 0. Then next is going to call some arbitrary function, and to do that a return pointer to line 6 is pushed on the stack, and the arbitrary function can do anything with the rest of the stack and use it at its stack frame. After the calls return, F changes x to 1 and calls the adversary again. And this is where the issues start. So if local state encapsulation is not enforced, then the arbitrary function would just change x to any value and violate the assertion when it's going to return. On the other hand, if wire-bracketed control flow is not enforced, then the adversary could keep a copy of the return pointer to line 8 anywhere in memory, so either on the stack or on the heap. So in this drawing, I kept the copy on the stack. Then the adversary can decide to call F instead of returning. And since the variable x is static, then that means that when f is called, then it's going to set x back again to 0. And the adversary is called again. But this time, the adversary has access to the return pointer to line 8, since it kept a copy from a few steps before. So then it can go back to the assertion, and the assertion is going to be validated since x is now set to 0. Now let's see what temporal stack safety is. In this example, main has a local variable x, and it's going to pass its reference to f. F uses this reference and store inside a reference to its own local variable z. The issue is that after returning, this reference stored in x is stale. Now, if the main function calls the function g, which used some memory padding, and calls the function h, which is used to write to some reference that it is given, it's possible that the reference given, which is x here, is actually going to coincide with where the return pointer is supposed to be stored. And in that case, if instead of writing 0, it was some other address, it could lead to jumping to some arbitrary code and then hijack the control flow. So as I said, the issue is really that it should not be possible for a reference to point to some stale location, as x does in this example. So while combining wire-bracketed control flow, local state encapsulation, and temporal stack safety would be great, I believe this is not sufficient to achieve complete stack safety. So what do I mean by that? I want to remark that when an element is popped from a stack, it should no longer be accessible through the stack, but that is not the case at low level. So for instance, consider this function f, which has some secret and passes its reference to a trusted function. The trusted function makes a copy on its own stack frame to do some computation with it before returning. So even if f clears its own stack frame, as is often done in security critical code, the trusted function may have forcoded to do so, and so a potentially malicious coder could then read what is left on the stack. So there is some form of use after free that has not been considered so far in those work that I mentioned. So to recap on the protection mechanism that have been proposed so far, Guard and others have proposed a calling convention using local cavities as can be found on cherry machines to enforce wire-bracketed control flow and local state encapsulation. But it does not enforce temporal safety nor protect against the use after free issue. And furthermore, it is not possible to use in practice as it requires way too much memory clearing. They then propose to use linear cavities to enforce the same purposes, but it is believed that linear cavities cannot be efficiently implemented in hardware. Then Nanopass and others have proposed so-called lifetime cavities to enforce temporal safety. I believe that they might be too costly to implement in hardware. And finally, Georges and others have proposed a new kind of capabilities called uninitialized capabilities and used it to improve on the first calling convention and made it fairly efficient. But the issue is that even if we combine a local uninitialized and lifetime capabilities, it won't be enough to solve the use after free issue. So let's see what those capabilities are. First, regular capabilities are just unforgeable tokens of authority. They have a given permission, such as read or read write or read write execute. they have a range of authority between two bounds, for instance B and E on the picture, and a current address it's equals 2. So for instance, in the picture, the cavities is going to have the permission P over the whole range between B and E, and it currently points to some address A inside of the range. And local cavities are, to simplify a bit, just cavities that can only be stored on the stack. And if we go back to the awkward example that I talked about, the issue was that for well-rated control flow, the adversary could keep a copy of the return pointer either on the stack or on the heap. But if the return pointer is made local, then it can only be kept on the stack. And as Skarsgård and Cortez have noticed, if F just clears the stack before calling the adversary, then the issue is solved, since the adversary will no longer have access to that copy of the return pointer. But this is obviously too costly in practice, since you need to clear the whole stack. So to implement this, Georges and Cortez have proposed unissuous capabilities, which are new kind of capabilities such that they have a regular permission on the initialized part between B and A on the picture. And they have a write only permission on the uninitialized part in gray in the picture. And the boundary is going to change each time that A is written to. So, and uninitialized cavities can be leveraged so that the memory clearing in the previous slide is not necessary anymore, which makes the current convention much more usable in practice. And finally, lifetime capabilities are capabilities that are annotated by a lifetime, represented by a number, which is the call depth of the function that owns the capability. So the idea is that capabilities with shorter lifetime cannot be stored using capabilities with longer lifetime. So for instance, if you remember the previous example that I gave, the variable z owned by f would be represented by a capability with lifetime n+1, and x is owned by main, so it would have a capability with lifetime n. And since n+1 is greater than n, then that means that it has a shorter lifetime and cannot be stored where x is. So this will obviously enforce temporal safety, since the issue was that x would point to a stale location, and this is not the case anymore. But to solve the use after free issue that I mentioned, we need to be able to stop the caller from keeping an alias with read authority over the whole stack. And even by combining all those capabilities, it is not sufficient to be able to enforce this. So what I propose is a new kind of capabilities that we call monotone capabilities, which I believe can be implemented in hardware. The idea is that since the stack is always growing in one direction, we can leverage this information. So in this picture, the stack grows toward the top. And so if a cavity can be used to read higher than another cavity, then this cavity has implicitly shorter lifetime than the second cavity. So for instance, in the picture, the cavity is uninitialized and can read up to A1, which is higher than A0, so it can be stored at address A0. But if it was not an uninitialized capability, it could be used to read up to E, and similarly, since E is greater than A0, it could not be stored at A0 either. So this obviously guarantee temporal safety, as it can be seen as some form of coarse lifetime capabilities. But we also obtain other property, which is that if a function owns a capability, a monotone capability with read authority over some range, then Necessarily, any other cavity also with read permission over that range must be stored above. So a courier cannot keep a copy or an alias of this over this range, and only callees can. But then this becomes the same issues as the return cavities that I presented earlier, and we know how to solve this. So to finish, there's a lot of exciting work focusing on protecting memory safety and especially the cross stack using cavity machines. But the proposed protection so far are not sufficient to achieve what I believe to be complete stack safety. And I propose a new form of capabilities to solve this issue. This is still work in progress, and we are now working on formally proving that this proposition really works. Thanks for watching.
All right, thank you. Let me, well, I see a raised hand right away, so please, yes.
Yes, hi, thanks for the talk. You mentioned a complete stack safety at the end. I was curious if there is a formal definition of this concept, or is it an informal notion?
It's only informal for now.
Okay.
I'm not really sure how. No, I don't really have any idea to formalize it correctly. I mean.
Okay, thanks.
I don't see any other questions on Clouder nor here on the chat. So maybe on this line, besides this, the property that François was mentioning, how do you plan to prove like that the capabilities capture what you stated? Like you mentioned several works, which I believe they all rely on fully abstract compilation. Do you plan to rely on that as well, or?
So not all of them rely on fully abstract compilation. So the works by Skorstogad and Cortez and the one by Aina and that will be presented on Thursday use logical regression to model what it means to be well bracketed and to have local state encapsulation. So that would be one way to continue, and by this time having a relational model. But it might also be interesting to follow the fully abstract compilation way. I'm not really sure yet which one is really the best between both directions, but we're exploring it.
All right, I think that I'll leave the floor to the chairs who will tell us how this continues after the break.
All right, thanks, Marco. We have, according to the program, a half-hour break, and then we will resume with the short talks. This will be in the same Zoom room, and the links should now be fixed on the website. Thanks to all the speakers and our session chair.
Hey, for the folks that are doing the short talks, can you please just stick around so that we can test your setup? That'll make our life much easier. All right. Stelios, so you want to give it a shot?
Right, let me try. I'm just gonna share screen. What do you think?
Yeah.
Blah, 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 blah. Can you hear my mouse? Can we hear my mouse moving?
We can't hear it, but we can see it.
Oh, you can see it, okay, because...
Does it make noise when you move or something?
Yeah, my mousepad is kind of coarse. It's like gaming mousepad, you know what I mean? So
no, we can't see it. You're good. We can't hear it. Yeah.
Awesome.
All right. Marco, do you want to hop on?
Yeah. Do you see stuff going on?
Yeah.
All right, perfect.
Yep, you're good. All right. Are there other folks doing short talks?
No, there's only these. Yeah, where is your long hair gone?
Well, Tamara said that 2 of her students might, but I'm not sure if they're here. If you're here, let me know.
Oh no, that's unfortunate.
Otherwise, we can all take a break and resume in 25 minutes or so. All right, folks, we have roughly 1 minute before we get started. Stelios, you want to bring up your slides?
Okay.
Awesome. Thank you. All right. So thanks all for sticking around. This is the last session. We have 2 fun talks from Stelio and Marco. The first is on a categorical approach to secure compilation, and a bunch of other things that he plugged in previous talks. So I'm excited to hear what you got. Before you get started, let me just click record so that we have this for later. Okay, take it away.
All right, thank you very much. So my name is Stelios, and I'm about to present this abstract study approach, say, to secure compilation, plus a few extras. Correction is not older work, it's actually new work that hasn't been presented before, but it is a short talk, so it doesn't matter. Anyway, I think most people from the audience by now should know what Morris-style contextual equivalence stands for. Let's go over it very quickly. E is contextual equivalent to Q if for all program contexts, the observable behavior of what happens when you plug and Q in the same context is the same. And usually this behavior is something very coarse. As Matteo said earlier, it can be something finer. So this is fully abstract, rather a compiler is fully abstract if it can preserve and reflect contextual equivalence. And it is well known that this is a tough relation to reason about directly. In fact, it is one relation that sort of haunts your dreams and devours your soul. It's that hard. So there's great incentive for more effective formal methods. And the idea is to give category theory a chance, if you will. So let's see what it brings to the table. So what was the main fundamental notion behind this approach? Was mathematical operational semantics, which you can see as the abstract analogy, the analogous notion compared to common structural operational semantics. In fact, it was partly developed by the same person, Plotkin. So what is this thing, mathematical operational semantics? First, you get 2 end-functors in a base category. You don't have to know what an end-functor is at this point. Just imagine that this is an abstract signature of sorts. And sigma here is a signature for syntax. It generates terms. While B here is a signature for behavior. For instance, for trace-based systems, for label transition systems, there's a B, there's a behavior functor that characterizes it. So having those 2 things, the semantics comes in the form of a Jesus law, which is a natural transformation of this over this. Again, no need to know exactly what this is. You can imagine, though, it's a polymorphic function that describes how order and how structure and behavior interact with one another. For the purposes of this talk, we're going to use this representation, lambda. Let's not explain the domain and codomain, which is a bit more general. So what's so good about this thing? Or rather, yeah, you should keep in mind that this is there is this abstract categorical analog of structural operational semantics. That's the main lesson here. No need to know the details. So what's so good about this kind of semantics? The good thing is that they are well behaved. In what sense? Now, this is a diagram here which is a bit obscure. So you can imagine the points here to be sets and the arrows to be functions. So you have this thing, you have basically H and G, which are both induced by this Jesus law, by this distributive law. And H is the inductively defined transition system. So just like the ones you would have if you had common structural operational semantics. G, on the other hand, is a denotational model, which is also induced by the same categorical construct. And what happens is that this function f, which maps programs their behaviors, somehow respects this whole thing here, there's this situation, this nice agreement between the operational model and the notational model. And usually you call this fully abstract semantics, but now the terms are not really accurate in this day and age, so I'm going to abstain from it. And you just have to remember that bisimilarity is a congruence only due to naturality, right? And this is a big deal that bisimilarity is a congruence, but course, let's explain first what a congruence is. Because congruence is a categorical term at heart, I believe. But I think most of the people that use formal methods have come across congruence one way or another, because it is ubiquitous in mathematics, and it captures structure preserving relations or predicates. There are also dual by simulations. So what do I mean when I say that most of you should be able to, or should recall seeing congruences? Well, when you come across terms, and I'm just showing you a bunch of keywords here, they're not the same thing, right? But when you come across those terminology here, this terminology, be it a compatible refinement, or which you can find in formal methods publications in the 90s, or logical relations, which is the most famous, the most significant method to proving full abstraction or other things. When you come across precongruence, when you come across terms such as fully abstract semantics, and then you also have the more abstract terms like relation lifting or algebra homomorphism. All of those terms express in some way or another preservation of structure. So let's briefly explain what this preservation of structure is. So I took this you have like two definitions here. I took one from the publication of A.D. Gordon, Bisimilarities, a Theory of Functional Programming. And the second one comes from a handbook by Bart Jacobs about coalgebra. But I could take, like the first one, you could find it in most of the works with logical relations. And what does it say? We take a relation called R, and we want to define its compatible refinement, R hat here. And what this says is that if you give me two terms, or rather two pairs of terms, which is related by R, then I can create R hat, and by saying that these pairs of terms over here, or rather these pair terms, and there's a constructor here, there's a constructor, this is a constructor. So if you give me two pairs of terms, I'm going to give you a paired term, so members of the relation of R hat. Now you also have this thing over here, which means that R hat implies R, and that is the definition of a precongruence I got from this publication. Now we switch over to the definition of relation lifting. It's basically the same components. You still need two pairs of related terms, and then I'm going to give you a related, a paired related term, if you like, over here. And then you also have this. This is the definition of a congruence, abstractly. Okay, but still there's the lingering question. Why should people in secure compilation care about congruences? So you have definitions such as this, contextual equivalence, where in some way, or rather explicitly, you quantify overall program context. Now, when you do that in this way, right? When you do that, the question you have to ask yourself is the set C algebraic? Meaning, is it freely generated by some signature? And usually, when you're talking about contexts as terms with a whole, they are freely generated. So they are algebraic. And I'm saying that if the answer is yes, then most likely you're making a congruence. This thing defines congruence. That is why in certain sources in the literature, you define Morris-style contextual equivalence, or rather, you define contextual equivalence in terms of the largest adequate congruence, where adequate means that there's some agreement with the observable behavior. And what we did in the paper, A Categorical Approach to Secure Compilation, last year, is that we showed how bisimilarity in a MOS specified system with mathematical operational semantics, right? That's MOS. Then two terms that are bisimilar are preserved. This relation is preserved by all program contexts, and this is a very strong property to have. And one, for instance, when bisimilarity really works for you, you really like it, and you really want to define contextual equivalence in terms of bisimilarity or trace equivalence, like Matteo did earlier, this is a really strong property to have, because now you can reason about contextual equivalence using this relation, right? So this is nice. Okay, we have all those. But let's talk about secure compilation. You have this representation of systems, right? So you have two systems now. You can basically just draw some lines over here and there and define what it means to have a well-behaved translation between these two semantics. And it comes in the form of syntactic translation, the behavior translation, because here in the abstract setting, you don't have to have the same set of terms between traces between systems, for instance. So they can have radically different behavior. And yeah, this diagram, you don't have to know exactly what it says, but it's something really strong in this case, which is somewhat of a drawback, because it says that the two semantics have to match each other step by step, abstractly. So it is something close to a bisimulation, but not quite. Much more abstract, much nicer. And it's just one criterion, right? Keep that in mind. So now keep in mind that this is there is an abstract description of a well-behaved compiler, and the idea was to basically put it to the test and see if this kind of definition can capture the insecurity of a compiler. So let's define really quickly, because there's not much time. Let's define like this while language. I'm gonna really skip the rules very quickly. So you have, yeah, sequential composition, you have skip statements, you have while loops, and you also have assignments. There we go. But so this is the assignment semantics in the high level. Now I'm introducing the low level in this slide. So this is the high level assignment. This is the high level behavior. Remember, you're gonna have a behavior in your system, and this behavior here, which is an endofunctor, but you should know that it just represents rather mutable state. And I'm saying here that you have a low level assignment too. Only your low-level behavior has this extra thing here, has this extra flag, this extra observable. It is like a flag register, because I'm saying that when you make a calculation, when you are you make an assignment, you're going to keep a trace of what the result of the action is. So yeah, you have an extra flags register in the low level. And you can now test the criterion, and I'm not going to explain to this, but as you can imagine, the identity translation, imagine that the terms are the same between the two languages, is not fully abstract, and the insecurity is caught by the criterion that I just showed you, by the definition of a map of distributive laws. So let's go quickly through it. No. Yeah, because basically the lower path is what happens when you run the program in the low level, basically the statement. You have a trace. When on the high level, you don't have a trace. You have like a zero. You just have the default trace that you chose to when translating the two languages. Now, if you introduce a sandbox and you decide to erase the flag, like 0, not only this compiler is fully abstract, but also it is the security. Rather, by definition, this is also a map of the distributive laws. So the definition of a distributive law catches the security of a compiler. And now, really quickly, I'm gonna skip this. This is a nice, though, example which I have encountered before with an earlier work with Cherry. Anyway, we're skipping this. So the bottom line is that maps of distributive laws do catch insecurities and confirm secure solutions. But there are major drawbacks here. One is that the semantics only give you this well-behavedness on bisimilarity, which can be too strong. Really, we want usually to reason about wiki relations, weak bisimulation, contextual equivalence, usually it's really coarse. And also, like I said, this notion of a compiler only matches between machines that match each other step by step. So we have a new work called Abstract Congruence Criteria for Weak Bisimilarity. We present adequate criteria that guarantee weak bisimulation being congruence. An early version of this paper is online. You can read it. The final version will be different, though. And I want to say, to also comment on earlier work, now we have criteria that give you a full abstraction result for weak trace equivalence, which I think pretty significant and pretty nice. Yeah, for now we can define this relaxed notion of a compiler, relaxed maps of distributive laws. And later on, we're gonna try to reconcile, or we're doing it right now, reconcile MOS with higher order languages, do case studies, and hopefully one day we're gonna have fully abstract semantics with regards to contextual equivalence. Thank you.
All right. Thank you so much. Other than the fact that you used up your whole time slot. Okay, so we don't really have time for questions. If you do have questions, maybe we could just take them off chat if that's okay. And we can move on to Marco's talk on contract-aware secure compilation.
Okay.
So either chat on Zoom or Cladder. Sorry to hold off early. So Marco, take it away.
I think, okay, now I can share. Okay. Can you see the slides?
Yep, you're good.
Okay, great. Okay, so I'm not really going to talk about some results that we have. Rather, I'm going to talk about some very early stage idea that I've been exploring with Marco Patrignani, and I think it nicely fits in the PriSC community. In particular, I'm going to touch about some of the topics that Hugo mentioned during the keynote, and in particular, what kind of stuff compilers can bring to the table when we are trying to fix microarchitectural effects. Okay, so let's start with processors. Everyone knows processor at the core of all our systems. They effectively run stuff. In the end, everything passes through a processor at some point. Recently, however, researchers discovered a gazillion of new attacks in the last, few years. Each of these attacks come with a very fancy logo. People can be very creative. And the key idea is that these attacks target processor security. And in particular, they do this by exploiting microarchitectural side effects that result either from processor optimization, such as processor optimizations on how instructions are executed, such as speculative and out-of-order execution, or the side effects introduced by internal buffers and caches that in the end are invisible at the instruction architecture level, and all the side effects are actually exploited to compromise security of applications. So the short summary is kind of processor security is a bit broken. So in this context, what can programmers do? Well, to write secure programs, programmers need to take these side effects into account, and they need to somehow program defensively to avoid potential leaks. And this is already a daunting task. To make this even worse, unfortunately, there is no unique reference for microarchitectural side channels. And the reason for this is that different processors and different generations of the same processor have differences in the internal microarchitectures, and somehow in the end, they provide different levels of security. So just to give you a concrete example, even a simple instruction like CL flush, which triggers a cache flush, has in the end different microarchitectural side effects on various generations of Intel processors. Okay, so the summary is that we have a ton of side effects, each depending on specific processors and specific internal details of what's going on. And programmers have to take all of these side effects into account when writing programs. And well, this is simply unrealistic. We cannot and we should not expect programmers to manually tailor programs for specific processors and for their security guarantees, I would say insecurity guarantees. And this is where we believe that compilers can help fixing this problem. And in particular, compilers can bridge the security gap between the ISP level and the microarchitectural level with all these side effects without really requiring programmers to think too much about all these side effects. And yeah, and somehow our idea is that compilers should target specific processor security guarantees, and they should leverage these guarantees to produce secure code. Concretely, compilers should generate different target programs depending on the specific CPU that we want to run the program on, and depending on in the end on which attacks these CPUs are vulnerable to. So if we can get this kind of smart programmer that can fix the microarchitectural issues for us, then, programmers can simply focus on program level security. For instance, programmers will have to ensure that secrets are not leaked under the source semantics, while compilers will take care of microarchitectural security concerns, like, let's say, preventing leaks due to caches or due to speculative execution. Okay? So this is a very high-level vision. We don't really have too many results in this direction, but we do have a clear view of, or we do have a reasonably clear plan to achieve this. And this is what I'm going to discuss in the few next slides. Okay, so the first thing that we need is, I've been talking about microarchitectural side effects. Well, we need a way of modeling this kind of side effects, and we need a way of expressing the processor's microarchitectural security guarantees. And for this, I'm going to use something that we call Arbor software contract, which we recently introduced in an open paper. And the key idea is that contracts are an abstraction for distributing security obligations between hardware and software. And in particular, we focused in this paper on information flow properties. So this is the setting that I'm going to play with in the rest of the talk. So contracts precisely capture hardware side channel security guarantees in a way that is mechanism independent, so it doesn't rely too much on what's really going on internally inside the hardware. And the framework consists of, let's say, two main components. First, we have a model of a processor. So processors are modeled using a hardware trace semantics, where observations model sequences of microarchitectural state that happen during the execution. So, yeah, for instance, we have these red curly brackets that is the hardware trace semantics. So this would say that, executing the program P on the CPU, starting from an architectural state, initial architectural state sigma, then produces this sequence of potential microarchitectural states. And the second big component of the framework is contracts. So contracts are modeled as labeled semantics for the ISA language. And the key point is that the labels in the contract expose security relevant microarchitectural events during the execution. Let's say, for instance, the address of a memory access or the outcome of control flow statement. Now, given these two components, given these two models, the framework precisely captures the notion of a processor satisfying a contract. So this is actually let's say, the semantic meaning of contracts. So we can state that a processor satisfies the contract, and we can prove that the processor satisfies the contract. The intuition behind this notion is that whenever a processor satisfies the contract, then initial architectural states that produce the same contract traces then are guaranteed to be distinguishable according to the hardware trace semantics. Okay, so the short point is contracts provide a concise way of semantically characterizing, let's say, leakage models or and processor guarantees. Okay, so concrete example. What we did in that paper is we defined several contracts for modeling guarantees provided by different hardware level countermeasures for preventing Spectre-style attacks. So we came up with a bunch of contracts which are shown here in the lattice. So each of these contracts capture a slightly different leakage model. And just to give you some examples, for instance, we have, let's say, a bottom contract that corresponds to a CPU that would leak everything, top contract corresponding to CPU that leaks nothing, and a bunch of things in the middle, for instance, sexcity, which is the standard, let's say, constant time observer, where we can see addresses of load stores and instruction fetches, secarc, which is a slightly weaker version that discloses more information, and spexcity, which is, let's say, which is very similar to the speculative constant time model considered in the talk, considered in the talk previously. So constant time extended to speculative execution. Okay, so we do have a way of expressing contracts. So the key point now is, what can we use contracts for with compilers? Well, the key in our approach is making the compiler contract aware. So the point is that the compiler is going to be parametric in a set of contracts, where each contract effectively defines a different target language for the compiler. So all the contracts target the same syntax, but they will have different trace semantics that result from the details of the contract, and let's say the leakage model. So now we can lift the existing secure compilation criteria to contract-aware compilers, and we simply say that a contract-aware compiler is secure if it is secure for all the contracts that are supported. Okay, so if you consider a property like constant time, now we can have different contracts, such as those that I've shown you before, and we can prove that the contract-aware compiler preserves constant time for the set of contracts, right? So depending on the underlying guarantees of the processor, we will know that the compiler satisfies, still preserves constant time. Okay, last slide. What I want to do here is try to put everything together by illustrating what it means to construct an end-to-end secure system using our contract-aware secure compilation approach, or CASCO for short. And as an example, I'm going to focus on constant time. Okay, so there are 3 steps. First, the programmer needs to ensure that the source program in constant time is constant time in the source language. Okay, that's the thing that the programmer should focus on. The next step, well, we have a CASCO compiler that ensures that constant time is preserved for all contracts under consideration, where each contract, as I said before, captures a slightly different leakage model, such as CPUs with and without speculative execution. So the key point here is that the secure compilation proof only has to go up to the contract level. There is no need to actually play with details of the underlying hardware semantics. And the final step is that, well, hardware engineers will provide contracts that each of the processors that we want to run our system on will satisfy, ideally together with proofs. And the key point is that by combining all these 3 proofs, so source program is constant time, compiler is preserves constant time for all the contracts, and a specific hardware satisfies the contract, then we can derive that running the program on the underlying hardware still preserves constant time. Okay, so running the program on the hardware runs in constant time. So the key point is that CASCO allows you to split the security proof for an end-to-end system in different blocks, right? And across different actors, so that, at least my opinion, all these proofs are simpler than having to carry out the entire proofs end-to-end. Okay, I think that's it. So as I said before at the beginning, this is a very long-term project. We don't have many results yet, so we just started exploring it, both at the hardware and compiler levels. We do have an extended abstract with a few pointers and a few more details on the idea, and I'm happy to have a chat about this project and any questions you might have.
Awesome, thank you. All right, folks, please type up your questions or raise your hand, or even just jump in. I guess while y'all think of some questions, I have a few questions, I guess, but I'm gonna maybe try to think through one. So I guess I'm thinking of like a real compiler like Clang or GCC. So what does this mean in like an optimization pass? Like, do I now need to reason about these contracts in my optimization passes, or is this something that I can like put off till later, or I guess like have you thought through that kind of?
Not too much, let's say, but I mean, I would say that, okay, I guess it depends on the kind of optimization process, but I think for a bunch of things, you can probably simply do the compilation down. I don't know, in Clang, you can simply do the compilation down to, I mean, let's say, I do see contracts as something like the machine-dependent passes in Clang. So you can do a bunch of optimizations beforehand, and then be like a deloring. Spatialize. Yeah.
Got it. Got it. Thanks, Matteo. Go for it.
Yeah. Hi. Can you hear me?
Yeah.
Yeah. Okay. Thank you, Marco, for the great talk. And my question is whether I'm not sure if this is relevant, but my question is whether your contracts are composable in some sense. I mean, if you have something that satisfies a contract and then you build something else that satisfies, well, actually, you have two contracts. You build a thing that satisfies a contract and the same thing satisfies the other contract. Can you say that the thing that you built satisfies both the contracts or not? Or I don't know.
Okay, I think it's a great question. I guess the most honest answer is I don't have a good intuition yet about this. So the nice bit is contracts. So as I showed you at some point, you can actually build a lattice of contracts. So I do expect that there will be a way of composing stuff and potentially. So I think you can compose contracts easily. Composing proofs is slightly more difficult, or I don't know, composing compiler passes is slightly more difficult.
Okay, thank you.
All right. I have a bunch more questions, but I think I'll just talk to you offline.
Yeah.
So, all right, this closes PriSC 2021. Thank you all for sticking around and for participating. I think this was a lot of fun, given that it's online and on Zoom and on Clouder, which are all in some degrees of experimental status. Next year, hopefully we can do this in person and, I don't know, maybe grab a beer or something together and chat about more ideas. But please all talk to each other. There's lots of, I think, cool things that came out of this. So with that, I don't know, Jonathan, if you have anything else to say, but thank you all for coming.
Yeah, I just want to thank everyone for coming. It's been like quite challenging to organize this, and like everyone played along really nicely. We had all of the videos in time, and like we had a pretty steady attendance. So it was really nice to see around 40 people minimum throughout the entire day. So thanks everyone for making sure this year was a success, and we look forward to seeing you once again, hopefully in person next